uh, how they are tied together globally and why they are tied together globally. Yesterday, we talked about frameworks all the way from the global to the institutional level. So I have the daunting effort of trying to put those into context and again, frame why it is so incredibly important that we think holistically about the tools, the frameworks, and the communication systems that we have across the life sciences to govern the risks potentially posed by dual use research of concern, but also to think more broadly about what those risks look like now and in the immediate future. The estimate is that between 2015 and 2025, the amount of data generated annually by the life sciences across the research and development enterprise increased by 2 to 3 orders of magnitude. That is increased by somewhere between 100 and 1,000-fold every year. And that the amount of data now being generated by genomics alone um, exceeds, we're measuring it in exabytes every year, which is, it goes exabyte, terabyte, gigabyte. It is enormous amounts of data being generated that are not just standalone. Um, when I was a student, research projects often generated data, but that data was frequently very specialized and really self-contained. It was isolated to a specific project. It had a specific set of data that could be accessed by others. Now, research projects generate a single research project may encompass epidemiological data, genomic data, other biological data. There may be operational data related to the equipment in the laboratories and the analytical um, algorithms being used to analyze. Altogether now, data is the most valuable commodity that research produces because data and information can easily be transformed into real world um, physical products. If you think about genomic data being, for example, used to create a vaccine or a therapeutic or a diagnostic, information and data are now part of that overarching environment that we have to think about when we think about biosecurity and the potential uses and misuses of dual use research of concern. The data itself, the information itself, is in no way inherently dangerous, right? Information is not dangerous any more than a sample of a pathogen is inherently in the right hands for the right uses dangerous. It doesn't fall neatly into safe and risky. Instead, really what we talk about when we think about protecting data and protecting information is risks that arise in transferring information. Scientific transparency is absolutely critical to the research enterprise at the national level and at the global level. Only by the transparent sharing of information and data do we build on past knowledge, skills, and tools to keep advancing the work that helps us improve health, protect the environment, improve sources of energy, and overall make it possible to continuously uh, augment the way we live, our well-being, and our ability to harvest sufficient food, to have sufficient energy, and to be able to thrive on this planet together. So sharing that information is absolutely critical. But in sharing, there are issues about how information is accessed, how it is forwarded, how it is interpreted, and how it is repackaged. This is a very broad overview of the way that information is often transferred in life science contexts. And the reason that I bring this up in the context of this workshop on dual use research of concern is that all of these are channels in which legitimate scientific advances and knowledge are shared with others who will use that information to continue to advance their work, to advance their own work, to identify opportunities for global collaboration, information, and knowledge sharing that, again, help us identify threats to health, to detect them more rapidly, and to counter them. At the same time, the question of how that data is received and used depends very much on the receivers of knowledge, their beliefs, their goals, their capabilities, how prepared they are to use that information, either for purposes of transparent and open collaboration or to exploit that information for their own purposes. And purposes can be um, negative without necessarily being nefarious. What I mean by that is frequently when I've shared this talk in other settings, and I'm in a room full of people, I've asked how many people have ever had their own work, their own scientific progress plagiarized or used by others without their knowledge or permission. The issue is not, do others access and use your knowledge? It's, did they access and use the knowledge um, that was intended to be shared and in the way it was intended to be used? And increasingly, I find at talks that it used to, in just a couple of years ago, if I asked, have you ever had your work used by others, exploited by others? It was an occasional yes. Now I'm finding almost every workshop, someone who has had, as a life scientist researcher, the experience of having their own publications claimed by others and republished under the names of others, or having the data from their publications reproduced in proposals, in manuscripts, or in other settings by people who had not obtained those with fair permission and used them fairly. And obviously, when we think about protecting dual use research of concern, thinking about those channels of information transfer and who is consuming the information um, helps us begin thinking about how do we protect information and data as we move forward in a much more data-driven enterprise of life sciences, even as we are still thinking about how we protect materials, equipment, and knowledge. And that is made even more challenging by the richness of the ecosystem. When we speak of the research ecosystem, it is not obviously a single set of actors with a shared set of resources and norms and values. This is a graphic that I shared previously in Kuala Lumpur in June at the Global Health Security 2026 conference. I'm sharing it again, both because I feel that it helps convey the complexity of that ecosystem and because I burned a lot of electricity and water to make it, and I feel like we should recycle and be cognizant of that. Um, Now that we can turn electricity and water into images. Um, this is the just reminding us all that when we think about what governance looks like, that the research and innovation ecosystem that we talk about is comprised of organizations at different levels that have different roles in being good stewards of data and information and in protecting the products of research and innovation so that discovery can proceed through open and collaborative partnerships while protecting that data and information from being misused or misappropriated. It, we go here from the top, from international organizations. We've heard from many of our colleagues in the last day, and we'll hear again about international cooperation and global agendas. The role that intergovernmental organizations play is really to foster those spaces where we can set the agendas and set global norms so that we can identify the challenges and work on them together. National governments provide policy direction, regulations, and standards, as well as investing in research. Um, Research funding agencies, which could be international or national, provide the resources to do work. But in doing so, they also create the frameworks of what will be supported and have a role to play in governing the safety and protection of data and the products of research. At the institutional level, both research institutions and universities, which are a large body of specialized research institutions, play roles either in conducting research and advancing knowledge, or educating and training the workforce, the people who will be advancing research and discovery. And then finally, technical associations and practice associations, like the one hosting us today, help build the communities that share knowledge and set standards and advocate for integrity and excellence, the purpose of why we're all here. And together, those build on a set of shared resources that are here at the base of this tree representing research and innovation, because across this whole ecosystem, they feed progress and work. It's talent, collaboration, the infrastructure to do research, the norms to share knowledge openly, ethics and integrity, not just as a concept, but in practice, and then the resources to put those into action. Ultimately, they all share objectives. They all share the goals of, particularly when we talk about hostile interference in research and the possible misuse of data and information. They share the goal of preventing unwanted knowledge, information, or material transfer. Across that whole research ecosystem, we strive to promote open sharing of knowledge and information, but with the consent, the knowledge, and the management of those that produced it, particularly when you're talking about research that can shape a career. We all, I think, are well cognizant of the need to protect innovation for purposes of being able to protect intellectual property, patents, and other legal protections that allow the institution and the individual to benefit in managing potential conflicts of interest or conflicts of commitment. And those can be extremely complex in a world where individuals often now have multiple affiliations, or are partnering with collaborators around the world who themselves have their own networks of commitment, their own affiliations, allowing information and knowledge to spread widely through those networks, just like they would through, just like materials spread through the waters of an ecosystem. One of the goals is to prevent data breaches that could compromise research and systems. This is an issue that's often simply identified as biosecurity or cyber biosecurity, but the protection of data and information relies partly and certainly instrumentally on knowledgeable information technology professionals who know how to put technical protections into place to prevent incursions or hackers from having unwanted access to data. But that work only really succeeds if scientists are also part of it. The people who know what data is valuable, what data could harm a research program if it were disclosed without permission unwantedly, that could harm the program by taking away its most valuable asset, or that could be used by others to cause harm. Scientists are the people who know what data is valuable. Scientists are the people who know what equipment is connected to the internet or Wi-Fi enabled, or even requires Wi-Fi enabling to operate, as much of our laboratory equipment does now. Preventing data breaches is critical, and it's not solely the action of information technology. It's part of governance and frameworks all the way from the institutional level down to the laboratory level. Obviously, as a community, we have a common goal of assuring compliance with the protections that have already been put into place, either through global agreements or through national decisions to protect specific knowledge and technologies from unwanted transfer. And then finally, we all share the goal of preventing interference in research or the theft of information and data to protect mutually beneficial and transparent science collaboration. Scientific collaboration is the foundation of progress. And I'm just going to sum up by saying one of the title today that I was asked to speak on was this issue of governance all the way from the global level to the institutional level. There have been, again, presentations on specific agreements yesterday, and we'll be talking more today. So I'm not going to go into detail on each of those agreements, but what I do want to say is all of the global governance builds on a platform and a foundation of what happens not just at the national level, but at the institutional level. So I'm going to start at this bottom up and say that the institutional frameworks that help govern the protection of knowledge and data and the products of research, particularly research that is dual-use research of concern, that produces either data and information or materials that could be misused, that could be used to cause harm. Those institutional frameworks that are in place embed responsibility in daily practice. And for that to work, there has to be buy-in from the researchers at the institutional level, that a culture of integrity allows them to conduct their work, that allows their science to thrive. Those frameworks may be the biosafety committees that help review proposals, assess risks, and help researchers ensure that they have appropriate safety protocols in place. They can be ethical guidance, codes of conduct, or other practices to help researchers identify and pursue ethical behaviors. And they can be publication policies, reviewing policies to make sure that information that could be used to cause harm is not being unintentionally disclosed and shared, or that there's thoughtful consideration of what data should be shared and how and with which audiences. All of this is the foundation upon which national oversight and national standards are built to back up and provide the resources that institutions need, and to provide standards for how those institutions can define safe practices. And then over that are the global governance strategies, the international standards for safety, ethics, quality, and responsible conduct, data sharing norms that aim to make all data findable, accessible, interoperable, and reusable within the framework of treaties and agreements. And then finally, those treaties themselves. We've talked about the BWC and others yesterday, and I'm sure we'll talk more today. Those agreements to try to help governments at the national level set their own norms and to provide guidance. So with that, I'd like to thank you for allowing me to set the stage today. And I am certainly happy to answer any questions within the time that the organizers have allotted. Thank you.
Let's give her emojis. Thank you so much, Dr. Fischer, for your very insightful lecture. We appreciate you for this lecture. Please, if you have any question for her, you can drop on the Q&A session or in the chat box so that she can quickly respond to it. Do we have any question for her? Any question, please? She has spoken to us on the global collaboration, institutional governance, and building system for responsible life science. And she has emphasized that institutions must be, it's a global impact, and it starts from the institution, the individual, the institution, to national level, and to the global impact. So we are all responsible for the science that we are, the innovations that we are carrying out, and the way data in itself is not dangerous, but it is the way it is transferred that is the key. Please, do you have any questions before we go ahead and call in our next speaker? Faith, please let me check in the Q&A session on the chat box if anybody puts any question there, so we can quickly move ahead. Thank you so much, Dr. Fischer. We appreciate you greatly.
I think
we can move on to the next speaker. Is there a question?
Yeah, there's just one question in the chat box. And I just wanted to say, when you said prevent unwanted knowledge, do you mean classified? And I think that's an important question because it's not solely information that has been identified by a government or another body as being security information or national security information. I really mean transfer of knowledge in either unwanted transfer of knowledge when, say, there is a research collaboration with a partner. If the partner shares, if I partner with you on a research project and I transparently share my data with you about our work, protocols, SOPs, sequences, potentially personally identifiable information associated with research subjects, or other information that is considered sensitive, that if shared publicly could be misused. For example, if I have personally identifiable information for research subjects, there could be harm to those subjects if it's released. It could tell others about illnesses they have, which might affect their ability to get insurance or a job. That information could be held for ransom. If disclosed, it could be exploited by hackers. For example, if I take precautions at my institution to protect that information, but I share it with a collaborator who doesn't take the same precautions, that's unwanted knowledge transfer if they lose control, if a hacker, for example, downloads it. And this happens with more frequency now, all the time. If data is sent to another research partner without my permission, if my collaborator says, oh, I'm going to share this data set with someone else, for me, that's unwanted knowledge transfer. That's not how I intended my data to be used. And again, I hear more and more now from researchers who say, I presented at a conference and then saw my data in someone else's peer-reviewed manuscript or in someone else's proposal. That's unwanted knowledge transfer. So unwanted knowledge transfer can be a scientific malfeasance. It can harm personal and individuals. It can also be data that could be misused, like sequences or data about pathogens in DURC research. So I just want to make clear, it's not just research data that is security data. It's any data that the loss of control of the data could harm your ability to publish, your institution's ability to continue seeking funding, or could undermine the investment your funders, government or private, have made in your work in the hopes that it can be turned into products or applications that can be patented and become commercially available products. So it's a broad range of unwanted knowledge transfer, which is why our ecosystem really has to become more sophisticated and work together to recognize that the loss of data and knowledge is just as damaging as the loss of your pathogens, your equipment, your knowledge, and your protocols. Thank you.
Thank you so much, Dr. Julie, for that. Unwanted knowledge is not only research data, it can be any knowledge that you don't want to be shared. Thank you so much, ma, for your time. We appreciate you. So our next expert speaker is Dr. Soatiana Cathycia. She's a technical officer at World Health Organization, and she shall be speaking to us on World Health Organization Biorisk implementation and evaluation.
Dr. Soatiana, sorry, we can no longer hear you.
Hello, can you hear me now?
Yes, we can.
Okay, I can't hear you as well, but I believe it's my time to present now. Yeah,
Please go ahead.
okay, I'm trying to share my slides. So, yeah, can you see the slides now? Yes? Okay. Good morning, good afternoon, and good evening, everyone. So I hope you enjoyed the first day of the workshop and found the discussions yesterday valuable. I'm pleased to be back here with you today to introduce the WHO Biorisk implementation and evaluation tool, also called in short BRIET. And maybe a quick recap from yesterday's presentation. So we explored the WHO resource package, which provides really practical guidance to help countries and institutions promote the responsible use of the life sciences and mitigating biorisk, but also strengthening the governance of dual-use research of concern, and emerging technologies with dual-use potential yesterday. Today, we'll take a closer look at the BRIET and explore how it can support really the practical and context-specific implementation of these approaches. I also hope that at the end of this presentation, the participant yesterday that raised also some questions, and I didn't have the opportunity to respond, including a question around which ministries and stakeholders should be involved, but also a specific question around institutions that particularly those with limited resources, how they can begin their implementation journey. So as we will see, there is really a no-size-fits-all approach. So the BRIET is designed to help identify realistic and achievable entry points based on each institution or country's context and capacity. So I hope that I will achieve, to present that in a really comprehensive manner through the presentation that I will be giving now. So I will not extend on that. I took time to, go through the disclosure yesterday. So let's move on to the next slide. So as a reminder from yesterday's presentation, BRIET was really developed based on several key elements of the framework. It integrates the three core pillars of biorisk management, namely laboratory biosafety, laboratory biosecurity, and the oversight of dual-use research, while also incorporating the framework's values and principles and its a six-step approach. Here, I would like also to pause and really to emphasize on the fact that the BRIET draws on and links to a range of existing resources, providing user with really a practical and comprehensive tool to support implementation in diverse institutional and national contexts. It is important to make this statement because the idea beyond really BRIET when we start the development is to avoid duplication. So we made sure that this is another tool, it's always the case that will duplicate the existing one, but the idea is really that BRIET will added value when it comes to evaluation and implementation, and more importantly, focusing on strengthening dual-use research of concern oversight. Here in my next slide, I would like just to show here that this slide illustrates how the six-step approach has been translated into the structure of the BRIET. And what I particularly appreciate about this design is that it guides really users through a logical and systematic process, moving from understanding their current situation and capacities to identifying concrete practical actions for improvement. Here also I'd like to share that in the development of the BRIET tool, we have been working in close collaboration with Johns Hopkins for Health Security Center. So just to share that information here. So at its core, the tool is really designed to help, once again, member states and institutions identify relevant biorisks, assess their existing capacities, and to take practical steps to manage and mitigate those risks. BRIET also serves as a key implementation mechanism for the framework. So really to help also translate in a concrete manner its principles and value and the recommendations into really action. So just to summarize here, BRIET is about moving beyond simply recognizing risks. It's provide really a structured and systematic process to assess current capacity, identify priorities, and support continuous improvement, enabling really countries and institutions to strengthen biorisk management in a practical and context-specific manner. BRIET also serve several important objectives. So, and in this slide really illustrate the journey it takes users through. It begins with stakeholder and entity mapping, helping identify who needs to be involved and what roles different actors play at the national and institutional level. Then the tool guides user through the situation analysis, providing a structured way to really understand existing strengths, identify gaps, and recognize key challenges. And then building on this, a BRIET support risk assessment process, helping prioritize areas that may require greater attention or action. So based on those findings, BRIET now generates tailored recommendations and mitigation measures, often practical also option to address identified gaps while strengthening existing systems and capacity. Finally, the tool supports action planning and progress monitoring, helping prioritize activity, track implementation, and measure improvements over time. So we saw that also yesterday through the six-step approach. So to maybe summarize here that the BRIET really moves beyond assessment alone. It also provides a structured pathway from identifying challenges to implementing practical solutions and monitoring progress towards a stronger biorisk management and governance. So before looking at the output generated by the BRIET, I think it will be also very useful to understand how the tool was developed and how it is also how it operates. So just to highlight here that the BRIET was really developed through a rigorous and a highly consultative process, drawing from literature reviews, analysis of country experiences, expert interviews, technical advisory input, external peer review. I would just name, a few. But this approach really ensures that the tool reflects both the global guidance and real-world implementation experiences, which is really important to make sure that the tool is also fit for a purpose. And to make the tool practical and also user-friendly, the content was streamlined into a focused set of questions. So I will come to that in my next slide. But the idea here is to make sure that BRIET allows a really user to go through, a comprehensive while remaining, a manageable set of tools. So usually when it comes to tool, we have a bunch of, questions that are lengthy. As I said at the beginning, the idea here is to not replicate or duplicate what exists already, but to provide an added value tool that will complement what exists, but will provide also useful guidance to address the oversight of tool use research. Tool use research of concern when it comes to the three pillars of the biorisk management. The BRIET does not rely on a single perspective, which is very important. So it brings, as said yesterday, together international recommendations, country expertise, expert knowledge, but also stakeholder validation, helping ensure that the tool is both evidence-based and practical. Maybe to also highlight here another key feature of the BRIET is its approach to risk assessment, as you can see here in the slide. So the tool considers risk through two dimensions, likelihood and consequence. So this really reflects an important principle of the biorisk governance, as many of you know. So some measures are designed to reduce the likelihood of an incident occurring, while others focus on minimizing the consequences should an event or an incident take place. So I think it's really also important to acknowledge that element, that effective biorisk governance requires attention to both dimensions, reducing the probability of harm wherever possible, while also ensuring that appropriate system and capacities are in place to manage potential impacts if they occur. Here, just quickly to show that this is how the BRIET process diagram look like. It shows how the different components come together in a structured and a practical workflow. The process is really designed to be logical, transparent, and easy to follow, helping the audiences to move from initial discussion and assessment towards evidence-based decision-making and concrete action. So just to say here that this is really a guide that provides progressive, key steps. And this is as well, as I said, since the beginning of my presentation, a tool that also provides a structured pathway. But in terms of question, if we look at the process diagram, so this will help really users move from three main questions. So where are we now, to what needs to be done next, and how do we track progress over time? Yeah. So moving on to the different, how the BRIET looks like. So you can see here in the picture on the, side of my slide, this is how it looks like in the platform. You have also the different steps on top of the presentation. So it starts with an overview, and then from the overview, you have a series of questions that would constitute the assessment aspect of the BRIET. And then based on the answer of those questions, risk score output will be automatically generated, as well as the capacity output. And then at the end, you will have a set of priority actions based on the different answers, risk score output, and capacity. So this slide is also very important, and maybe will provide more information as well, more granularity on the two main audience targeted by BRIET at national and institutional level. So one question that often comes up is what exactly do we mean by national government, for instance? Who exactly should be involved when it comes to the BRIET National? So this guidance may be also useful. Of course, the list shown here are not exhaustive. Countries and institutions should adapt them to reflect their own structures and governance systems. So you can see here the list for the BRIET National and for the BRIET Institutional. What is really important is that these two versions are complementary. One focuses on the broader national system, while the other focuses on the individual institution, but together they provide a more complete picture of biorisk management and the capacity need. And this is also echoing the presentation, one of the slides from Julia, that the structure from institutional to national to international is really also very important. So when it comes to the main topics covered by the BRIET across both versions of the tool, so you can see here for institutional, the assessment include 32 questions across 7 categories, focusing on practical areas such as compliance, risk mitigation, transparency, incident reporting, and workforce training. And at national level, you see that the assessment expands to 42 questions across 8 categories and covering broader governance elements such as legislation, oversight processes, stakeholder engagement, resource allocation, implementation of international standards, etc. Here, there are slightly, difference when it comes to the specific question, but both versions follow the same objective, helping users understand their current capacity, identify gaps, and prioritize areas for improvement. So to conclude on the presentation of the BRIET, really BRIET is first and foremost a self-assessment and a capacity building tool. It helps user identify strengths, recognize gaps, and prioritize opportunities for improvement. The tool is voluntary, so this is very important, flexible and adaptable, supporting the audiences without imposing a specific model or maybe additional compliance requirements. Another key strength is its collaborative approach, so bringing together stakeholders from different disciplines, sectors, and level to support effective biorisk management. And finally, just maybe to say here that BRIET is once again a practical and supportive tool that will help really to move from, situation analysis, stakeholder mapping to risk output, risk capacity output, and priority action, but also most importantly, to foster continuous improvement. So I would like now to walk you briefly through a live demo of the BRIET, but maybe just because I'm showing here the QR code, just one quick note before we move on. So the BRIET is currently pending final WHO publication clearance. So once that process is completed, it will be officially launched on the WHO platform. For the moment, the QR code that you see here that takes you to a testing environment, but the tool itself, it's already finalized. So what you are exploring today, what I'm going to show you today, reflect the version that will be made publicly available as a formal official on the official release of the BRIET. The content, structure, and the functionality of the tool will remain unchanged. So just to make that clear, so if you, maybe I will give you a moment to scan, so then we can go through the platform together. With that, maybe I can go directly here. Here, where is the BRIET? I can't see. It's in here. Okay. Can you see the screen still? Yes?
Yes, we can see the
Yes.
QR code.
Okay, thank you. So let's start with the, maybe I can do like this. Yes, so let's start with the demo. I hope that you were able to scan the QR code and now have the BRIET on your device, at your phone or maybe iPad or whatever. So on the BRIET landing page, normally before accessing the tool, you will be receiving, through a box to ask you to agree to the terms and the data privacy condition. Because I use this link so often, so for me it didn't show, but normally that's the first thing that you will see on the landing page. I think one also important point to highlight is that the information entered into the BRIET is not stored or compiled in the WHO database. So this is very important statement to make. The data remains with the user, stored locally in the user's browser, who can choose to save, to export, or to share the result as needed. So this really helps ensure ownership, confidentiality, flexibility in how the assessments are conducted and used. I think this is really important to emphasize here. And here is the main entry page of the BRIET. So as you can see here, it is organized really into a clear section, including, the rationale, the objectives, methodology, helping really user navigate the process step by step. And this introductory page provides all the necessary information when it comes to understanding the tool. I think a particular also useful feature is here, the help function, which provide guidance on key function, including also if you are stuck at some point, so you can go there to see how to, continue navigating smoothly the tool. This function here at the top of the platform remains throughout the different pages of the BRIET tool. So it is accessible across the different steps of the BRIET tool. If you go down here, you can see also the two versions of the BRIET, so the BRIET National and the BRIET Institutional. I want maybe to open quickly the methodology to show you one important section. So as I said during my presentation, BRIET really leverage on existing resources. So these are a list of those, existing guidance and tools that help the development of the BRIET with the spirit to avoid duplication, of course. So now maybe for this demo, I will click on the BRIET National.
1 minute, Soatiana, can you hear me? We can't see your screen for the demo. We can
You
only
can't.
see, yeah, we can
Okay.
only see your shared screen, your presentation.
Okay, sorry. Maybe I will share again because I moved from the. So let me know if you can see now.
Yes, we can see it now.
Okay, so just to go back, I will not repeat, but to show this is the introductory page, as I said, so you have everything. And I clicked here on the BRIET National to provide more, in-depth information on this specific version of the BRIET. So as you can see here, these are the different steps that the BRIET will take you for this BRIET National. And this will be done in a really, let's say, progressive manner. One element I want to also highlight here is that here there is opportunity always to retrieve a previous evaluation, or if it's your first time to start a new one. So this is the place that will help you navigate that. This page will provide, basic information. So you'll have to fill the name of the evaluation. And for instance, if this will be done in a regular manner, let's say annually or twice a year, you can maybe name the folder accordingly. You will need also to select the countries and area. This will help at the end of the assessment to link this implementation and evaluation result into the self-party annual self-assessment, self-party assessment for the annual review of the IHR. So you will have the corresponding also score there. So I will show you that at the end. You will have to fill the date, add some description to allow you to retrieve easily your folder. And here at the bottom, you can see that there is always a possibility to return to the main page or to save. Here is the place to save the current evaluation if you have to stop at some point. Just also to explain here that because this is a testing environment, so you still have this random values box to click to allow you to move to the different steps of the BRIET tool. But once we have the formal, release of the BRIET into the WHO platform, this functionality will disappear. So here, let me click on next, and then we land on the questionnaire page, and this is the assessment per se. So as presented in my presentation, this is organized into categories of questions. So for the BRIET national, it is we have 8 categories with different series of questions for each of them. Here, just to present as well that you still have enough information to understand the question, so you have that possibility. Each question comes with also a list of predefined answer, but there is always opportunity to come up with additional answer if you feel that in the list there some specificity are missing. There is also possibility here to share the question. So let's say you start to use the tool, but some critical stakeholders are missing in the table. So you can still have the opportunity to share this question. So that's for the specific question. You can copy and paste if you want, or share via email and add the email address of the person that you have in mind. Here, it's also the opportunity to share maybe multiple questions or all the questions, so you can do that. You can share here the selected question. Once again, it will go directly through the email of the person. Here, you still have guidance when it comes to the stakeholders that need to be involved, for instance, for specific questions. So this is the list. Once again, this is really tailored to the context and the system in place for each individual countries. So there is a need always to see if some critical stakeholders are missing there. I will close here. Another key element is to pay special attention on the pillars. So as you can see here, there is opportunities based on the question to select the pillar, or at some moment the pillars are predefined because this will address specific pillar within the 3 core pillars. So this is very important also because that will help you really to make sure that you can capture the capacity that is weak, that you consider as weak, where you can really act with priority action for improvement. So I will not go through all the questions, but here, for instance, this is a preset pillar for this question. So here you don't have the possibility to select, and then you go through, the list of response, and you can add, additional notes. Another, maybe on this page, and we will move to the next page, is this box on additional information. So here you can still also look at more guidance. So for instance, for this question, the cross-cutting themes is listed here. You can still have more orientation when it comes to the stakeholders to engage and to get, the answer for the assessment. So you have the list here. You can also look at the existing relevant tools and the useful reference. So when it comes to the BWC implementation measures database, you can also look at the reporting of your own country to have some kind of idea on where you are and what's this result will mean for the future. And lastly, maybe to show here, this is where the values and principles comes into force. So for each of the question, we made the effort to highlight the specific value and principle, but of course, this is adaptable to the different contexts. So it is possible to select more than one value and principle, or to change the value if you feel like this is not really in accordance with what exists in your country. So moving on from that, let's move to the next at the end. So to the next page. And you can see here, you can go back and still navigate as you wish. Now we land on the risk score output. So you see directly the overall biorisk score here with the specificity for each of the pillars. So as I said in my presentation, this is automatically generated based on the answer that you provide on the different questions. And then down here, you have more granularity when it comes to the likelihood and the consequences. So this will provide also a better visual when it comes to the granular data attached to the overall risk score. Moving on to the capacity output. So this will be also automatically generated. So it is categorized into high, moderate, or low capacity. What is important here is that the capacity that needs specific attention is, of course, the moderate and the low capacity, because there where you can really take action to improve the situation when it comes to the progress that you will track later on. Here, just to show that there is always a possibility to add capacity for each of the categories. So if you click here, if you feel like something is missing, then you can still add, and this will be taken into account in the priority actions. Moving on, so this is how the key action would look like. So once again, this is pre-defined based on your answers to the different questions, and you have the granularity of the different actions based on your risk score and your capacity output. I will not go in details on that, but you have that element. And once again, if something is missing, you can still have the opportunity to add there. Once you click on the finish, then you will have the result page. So this will provide you with the summary of the evaluation. So you click here, you will have what you have completed in the previous step. It will provide you those summary. there is also opportunity to export the result of your assessment. You can choose to export a brief summary. So the brief summary is mainly to show the risk score output. That's the brief summary. But if you wish to export, for example, the complete assessment, so we can maybe let me here. I hope you will see. Can you see the screen now as I move to another?
Yes, we can see the screen.
Yes. So here is the really the brief summary. As I said, it's only about the risk score. But when you go into the complete, so as you can see here, everything is on my local computer. So I can click here, and then you will receive the full assessment completed. Just maybe to show you for the example of Algeria. So you see at the end here, the state party self-assessment annual reported. So this is the data that was shared with WHO as part of the IHR, and you can see the date here. So this is accurate data on that date, and there is a possibility to really see the situation of the country and to improve, taking into account also the broader elements. So this is my presentation. I hope that that was clear, and that also provide more, insights for the participant. Thank you very much. Happy to take any questions, and back to you, Madam Chair. Thank you.
Wow, thank you very much, Dr. Soatiana, for that beautiful presentation. That was quite detailed, and the practical demonstration of the WHO BRIET tool. So thank you so much. We'll be happy to take questions. I don't know if you do have any question in the Q&A session. Please let me know if you have questions, and ensure that all questions are directed to the Q&A box so it doesn't get lost in the chat.
On the animal and environmental health, or animal health.
Ensure that all questions are directed. Okay, there's a question here. It says, thank you for this excellent presentation and developing new tools for biorisk management on national and institutional level. I have one question, that how can BRIET be validated in a conflict-affected settings where institutional capacities were severely disrupted, e.g. US, Iran, and Gaza, etc.?
So as I said in my presentation, without going into deep on the let's say political aspect, but the BRIET is once again, it's a self-assessment and voluntary. So it will really depend on any stakeholder or party that find the priority to move into the strengthening of the governance, but also to foster the responsible use, to use the BRIET. This has no compliance, requirements. So the idea here is really to start with assessment, so to see the situation, and then from there to walk through a feasible and a practical manner. So I don't, when you listed the list of country, I don't know exactly what you have in mind beyond the question, but when it comes to the technical, let's say, implementation of the tool, this is applicable for any countries or setting that see the importance of using the tool for the goal that I've listed during my presentation. I don't know if I responded to your question, but yeah, that's what I can say for the moment. Thank you.
Thank you very much for that response. We'll be taking one more question and then the rest will be answered via email because we are way behind schedule. So this question says, how important is BRIET as regards dual use research and the safe use of data? How important is BRIET as regards dual use research and the safe use of data? Thank you.
Yes, so the BRIET can be used for also, because we had the presentation earlier, Julia's presentation around data. And when it comes to data, what we have in mind is, for instance, in terms of stakeholder group, that could be publishers, editors, but also the scientific or the researcher or the scientist that is running the research. So the BRIET is applicable to all of those stakeholders, of course. When it comes to that, maybe the BRIET institutional could be helpful, but it depends, because when we talk about data, maybe the national government can also have interest to, use the BRIET national and to go in deep into that. So just to summarize, my response is to say that the BRIET is the operational harm of the framework that will help really to put the global guidance framework into more practical and concrete manner. So I would like maybe to, my presentation was a little bit fast because of the time, but the QR code is there. If you take a moment to go through, the question, maybe you will see that how the BRIET could really help those different layers to come up with, solutions. Thank you.
Yeah, thank you so much. That was beautiful. Yes, the recording of the workshop will be made available on our YouTube channel at Biosafe Advocacy Network on YouTube. So we can always go back to watch, and with the permission of our speaker, some of this resource material will be shared across all registered participants. So you can always go back to check these things and ensure that you watch it and use it. Thank you so much, Dr. Soatiana, for that presentation. Please let's appreciate her. Let's show her some love. We are grateful to have you. Thank you for presenting at our workshop day 1 and day 2. Thank you so much. We would like everyone to please fill an evaluation form that is available in the chat. If you have not already done so, there's an evaluation form available in the chat box. Kindly fill it. It will be posted again. Please ensure that you fill the evaluation form so we can know how well this workshop is doing and what you've learned. Thank you very much once again to our speaker. Right now, we'll be moving on to another session of the workshop. We all know that artificial intelligence is rapidly transforming the life science. It is creating a lot of exciting opportunities while we are learning new things. And it is also introducing some new ethical and biosecurity challenges. And to guide us through this important discussion on artificial intelligence, it's my pleasure to introduce Dr. Sharon Malonza. Dr. Sharon Malonza is a full-time medical doctor working for the National Health Service in England as an academic foundation doctor on the Specialized Foundation Program. She has protected research time built into her training, giving her early exposure to academic medicine alongside her clinical rotations. In addition to her clinical commitments, she undertakes research at the intersection of AI and biosecurity. She was an AI and biosecurity fellow at the ILINA program, which is an African-led AI safety research program, and is currently a research contractor at the Center for Long-Term Resilience, an independent think tank focused on transforming global resilience to extreme risk And our research focuses on consideration to ensure equitable and verified access to AI-enabled biological tools. She'll be speaking to us on the theme that says, on the topic, artificial intelligence in the life science, emerging opportunities, ethical risk, and the dual use concerns in biosecurity. Please join me in welcoming Dr. Sharon Malonza. Thank you so much, Dr. Sharon, for accepting to speak. You now have the floor.
Thank you so much. Can you hear me okay?
Yes, we can.
Thank you for the wonderful introduction. Let me just get my slides up. Can we all see that clearly, my slides?
Yes, we can. Please go ahead.
Perfect. Okay, so today I will be talking about artificial intelligence in the life sciences, emerging opportunities, ethical risks, and dual use concerns in biosecurity. Now, AI is changing biology in a significant way. We are moving at a fast pace. Things that we used to take months to do are taking hours, and it's one of the most significant shifts we're having in our era in this time. Now, there are different ways AI is reshaping biology. We have tools like AlphaFold from Google, which can predict the 3D shape of proteins. We have genome editing and design tools that are able to interpret pathogens in human genomes at scale. And this is quite significant and useful, especially when trying to look at variants in disease and understanding drug resistance, and also in creating new technologies or targets for medications. So it is just fascinating. We're able to design new proteins, enzymes that did not exist before, and we're seeing a lot of changes and discoveries, not only in medicine, but across multiple industries. Now, this presents a lot of exciting opportunities, like I said. For one is faster and cheaper diagnostics, which is particularly relevant in low resource settings, like the global majority. So we're thinking about how we can shorten the time for diagnosis, but also reduce the costs. And we're seeing a lot of progress, especially from the clinical side, which is my background. Another thing is genomic disease surveillance. Early warning systems are an important thing we have to think about, especially when we're considering what AI can do for us in this space. And Africa CDC has created a pathogen genomics initiative, which is expanding the sequencing capacity in Africa. They've also established the Agari data platform very recently, which is the purpose here would be to enable countries to share pathogen genomes securely. Data sharing and is a big part of our day-to-day work. It's a big part of what all of you probably do when you think about your research in your classrooms and as professionals. And so it's a core part of also the developments that we're seeing and how AI is coming into play here. Like I said, the advancements in AI are not limited to medicine or to research. There's also improvements in agriculture and in the climate department and fields. So we're seeing a lot of AI-guided breeding. There's a lot of genetic work looking into how we can make crops more resilient and resistant to a variety of weather conditions. So this is very crucial, again, in the global majority as well, where we have a lot of cases of food insecurity. So there's a lot of progress and novelty in that field as well. And like I said, there is a lot of AI involvement in drug development, especially in the treatment of diseases like malaria, TB, sickle cell, which are diseases that are often neglected sometimes by the global pharmaceutical companies, but we're seeing a lot of progress in using AI to develop advancements in this area as well. So what do we mean by dual use? I feel like by now you are all professionals in what dual use concern means, so I won't harp on too much about it. But dual use in a nutshell is the same knowledge, tool, or technique can be used for both good or harm. And it really just depends on the user. Sometimes it is an unintended consequence of the distribution of these tools, knowledge and technique. So it can be misapplied. The same tool that we've talked about, all these wonderful opportunities like new medicines, vaccines, diagnostics, resilient crops, can also be used for misuse in making pathogens more harmful, in generating new toxins, and whether it's accidental or deliberate release of these pathogens, there's a huge concern here. And like I'm sure you've learned from undertaking the course for by WHO for this workshop, it's the important key step when we think about dual use research of concern is managing all of this through a shared culture of responsibility. And that's at the heart of all that we are talking about over the 2 days, is just thinking about what is my role here in the grand scheme of things, and how can I collaborate with others beyond myself to ensure that there's a shared culture of responsibility that promotes development and advancement, but we still have biosecurity at the heart of everything. Now, this is a specific example. In 2022, a drug discovery company ran a simple experiment. So they used AI, and the AI is normally used to search up useful, safe medicines, and it's told to make sure to avoid toxicity. And what they decided to do, and this was published back in 2022, is they flipped one setting of the model so that it was rewarded for toxicity instead. And so in 6 hours, the AI model was able to generate tens of thousands of candidate toxins, including nerve agents, and some predicted to be even deadlier. Now, while this was just an exercise, to be very clear, nothing was actually synthesized in the lab, but the lesson that we take away from this was very significant, that one line of code turned a beneficial tool into a harmful one. That's one big takeaway. Second is look at how fast the computing time that was. We're looking at work that previously, before AI, people would take loads and loads of time in the lab to even arrive at this conclusion before you can even test it in the lab setting. But AI has been able to speed this up. And this paper has really catapulted a lot of talks and thinking around how AI can be a significant dual use concern and pose a lot of risks. Now, what are the dual use concerns at the AI biology frontier? This is broadly speaking, and AI is a fast moving, advancing field. So even sometimes when we try to categorize AI tools distinctly, we're coming to find that there's more and more overlap between these tools that's making it even grayer and grayer. But one traditionally, or at the foundations of AI-enabled risk, we look at it in terms of two things. We're either lowering the barrier or raising the ceiling. So when we think of lowering the barrier, we're thinking about people who previously would not have had the access to specialized knowledge. And now AI is accelerating how quickly they're able to learn. And this is being seen more commonly with chatbots, so large language models, because this is something you can speak to the chatbot and it can quickly give you a lot of information, condensed information that it has scanned loads of literature to learn. So that is lowering the barriers of harm. And then when it comes to raising the ceiling, that is when we talk about more specialized tools, which for the purpose of this talk, I'll be calling AI-enabled biological tools. And these tools tend to be used by specialists, by experts, by people who have a background in science, are familiar with the workings of the lab work, have a deeper knowledge of virology or microbiology, and they are using specialized tools to help them do their work better. And that's anywhere from the ideation of a project to the literature review to what we've talked about, where it can help you to edit the genomes or look at the pathogen in more detail, to even lab automation and cloud labs, which are fast growing, where we have robot scientists and remote cloud labs, where we are moving from the theoretical, so where we have the LLMs and the BAMEs that are helping you to think through the project, to actually using AI and replacing scientists or in certain stages in the lab, with an aim of ultimately having autonomous labs where it's a fully AI driven system from start to finish. And there's a lot of progress happening in this area as well. Another concern is when it comes to synthesis screening. So DNA synthesis providers are a group of people who are screen orders for DNA to check for any danger or AI design sequences, to check for any sequences of concern. And we're seeing that growingly with AI is able to design sequences that might slip past the filters for these threats. I won't speak about this too much at length because I believe the next speaker, Neil Hamilton from IBIS, will be talking about this in more detail. So beyond that, we've talked about the opportunities, the AI-enabled risks, but there are also other ethical risks beyond the dual use concern. And one of them is the equity dimension. So sometimes for the global majority, the risk is not just about a malicious actor, but it is about the technology itself. And you have to think about things like algorithmic bias. These are things that are spoken at length about, that tools are being trained on non-representative data. So what does this mean for the African patients? If we don't have enough data from this cohort, then it will not be as accurate in this group of people. So for example, skin lesion AI missing cancers on darker skin because we do not have enough pictures of people with darker skin who have cancer. We don't have enough data on these things. And there's a paper that talks about how about 7% of gene trait associations come from African ancestry data, despite huge genetic diversity, but where we don't see a good representation of African genetic data in studies or in our databases. And again, this is a whole topic in and of itself that I will not harp on too much about, but we also have to think about data sovereignty, thinking about whose genomes, whose consent, whose benefit, when we are sharing biological data, whether it's on a national level, between departments, on a regional level, on a global level. There has to be a lot of considerations about governance risks, but also about ensuring that there's preservation of data sovereignty. And then lastly, dependence without capacity. So it is a challenge because a lot of the frontier AI models, a lot of the most superior models are being built in the global north. And that means that the global majority are deploying systems we did not build ourselves. And so it means that sometimes it is a challenge to detect the bias or contest wrong decisions. So as we continue to think about AI and, AI in the life sciences, this is something to think about as a person who is working in these spaces. Now, there have been many proposed measures to mitigate AI-enabled risk, and I like this image that summarizes different places where you can think about governance or measures that you can work through. So there's obviously development. So when we're building the tools itself, we make sure that we're training the tools well, that we are There are voluntary commitments. There's whether it's training the model before it's released or it's looking at the model after it's been released. And there's a lot of discussions there about export controls and publication norms. Thinking about risk assessment, again, this is more about the AI models themselves. So doing a lot of evaluations to check for the dangerous capabilities. And again, this is where technical AI safety work comes in. And there's a lot of work going on about monitoring for misuse and evaluating for harm. Transparency is an area that applies to all of us, where we think about, like I've mentioned, information sharing, about also reporting any vulnerabilities, which I'm sure as young professionals and scientists, this is something you always have to think about. If something goes wrong, is there a structure on how to report it and escalate it and ensure that these things are not happening again? Same things would apply with AI. Access management is a big area of focus within mitigating AI-enabled biorisk. And this is my particular area of interest at the moment. So I will talk a bit about structured access a bit more. And then we have cybersecurity, because again, AI-enabled risk is not just a risk within the life sciences, affect national security, they affect cybersecurity. So when you think about AI-enabled risk, it cuts across systems, it cuts across fields, and it has impacts that spill over into cybersecurity as well. And then investing in resilience. So thinking about model sharing infrastructure, compute, and countermeasures. So this is a case example that I like to think about, especially when we're talking about structured access more specifically. Now, most AI-enabled biological tools at present are open access, and that is supposed to be a positive thing, because the scientific community, as you and I know, believe in access, believe in sharing information readily, believe in collaboration and in exchange of ideas. But like I've explained in previous slides, there is a concern about the risk behind these tools. And so there's been an emerging proposal of restricting access or managing the access to these tools in order to ensure that the people who have access to these tools are verified and we are able to monitor them. And then hopefully this can reduce the risk associated with access. So that is, we can hopefully catch a malicious actor if they were to try and access these tools. So I like to use this example of, say, a new Ebola variant was to emerge in Uganda. And that's quite contextual and relevant at the moment, given the current outbreak. And local epidemiologists would like to use EbolaPred. So EbolaPred is an actual AI model. And they want to use this tool to design some antivirals. But let's assume that we have created managed access models for many of these tools, because that's the safe thing to do, that's the right thing to do. But for some reason, they can't access the managed platform because they don't meet the credential criteria. Now, I don't know if this is something that some of you have experienced before, not being able to access specific data or to access a tool or a service because you might not have the right email address, you might not have the right documentation. And so in this case, they turn to an open source alternative, which might have weaker capabilities. So my concern around this is that sometimes if we are not thinking about managed access for these tools in the right way, legitimate researchers from all over the world might not have access to the best tools. So that's one concern there. The second thing is we might lose oversight of these people. So open access tools are very hard to monitor. It's hard to monitor people if they are able to just download a model off of GitHub and put it on their computers. So tracking and monitoring users with open access tools is a lot harder than if we have them on a managed platform. So if someone has ill intent, then there is no oversight of this person. So that is a critical biosecurity and equity tension that I'm thinking a lot about, that restricting access to protect against misuse might actually weaken global defense capacity and reduce oversight if we do not do it the right way. So we have to make sure that access is equitable, and make sure that frontline detectors are not operating in the dark. So you and me, who have good intentions with these tools to bring a lot of great innovation, we have access to these tools, but we also have the firm foundations that, like we're doing through this workshop on biosafety and biosecurity, so that we use these tools responsibly. So who governs these tools? Where is our voice? We've had Dr. Raja talk at length about the WHO framework and the BRIET tool today, which was fantastic and really useful for me to know as well for my own learning. We have the age of AI in life sciences, and this is just a reference I can share after the talk for you to read up about the benefits and biosecurity considerations. We have DNA synthesis screening, which I've mentioned before. There's a lot of global efforts to ensure that we are screening DNA orders, because this is a real and tangible threat in terms of when we think about biosecurity, and make sure that we are strengthening the filters against these AI designed threats. So we also have the Africa Union NEPAD APET, which was launched to make sure that we can have some guidance on responsible AI in precision medicine, and this is more tailored to the continent's needs. And this is something you can read up more on. There's a lot of research going into this space. We also have the NIH's DSI Africa, which has put a lot of funding into establishing research hubs all over Africa to embed data governance and consent into AI health research. And obviously, biosafety law and biosafety committees happen at country level, at a university level, at a company level. So this is just a sample size of how many ways we can tackle AI-enabled biological risk and all of the work that is currently ongoing in this space. Now, like I said about equitable access, it's always important to think about how we will approach designing access measures within AI-enabled tools. And some of the propositions I have break down to 3 proposals, where it is competence over credentials. And the idea here is that with these principles, it's complementary to the propositions that have been given. That is, it is complementary to existing ways that we verify users. When you are being verified to get access to something, it's the same things: your name, your email, your grant history, access to your publications, all of that checklist. We already have an existing template. Can we think beyond these credentials, especially when we're thinking about a global majority context? So can we have peer attestation, where there's peer verification, or staged access models, where you give researchers a little bit of access and continue to increase the access based on responsible use. Infrastructure-aware design is an important second pillar, where we address the real barriers to AI-enabled tools, especially, again, in the global majority. Sometimes the barrier to access, making the tools open access, does not resolve the fact that there's not enough compute power. We don't have enough computing hubs, or we don't have consistent internet connectivity. So we have to think about low bandwidth interfaces, and multilingual support as well, which is really important. And lastly, distributed governance, where we have to make sure that we have bodies that are regional and contextual. They understand the local capacity, and we have regional certifiers who can ensure that this is performed correctly. So as I conclude, What you can do is, for one, learn dual use awareness, which is what you're doing by attending this workshop and doing the course, making biosecurity part of how you think about research in your practice. Pause before you publish. I know there's been discussions about thinking for a minute, could this method or data set be misused? Who is my audience? Should I take a moment before I provide all the details? What should be maybe behind a few access barriers? Like I've mentioned before, building African data sets ethically is a really important thing. Making sure we have rich, diverse, well-governed data will be fantastic for benefit sharing, but also on a global scale, where a lot of the pandemic and epidemic concerns are likely to come from the global majority. So we do need enough data and capacity to tackle the next pandemic. Joining biosafety networks, which you've done as well. Advocate for our voice, push for African representation in AI and biosecurity governance, and building a culture of care. So, like it's been said before, it's responsibility is yours and mine alike. So, in conclusion, Africa and the global majority as a whole should help responsible AI use in the life sciences safely, equitably, and on our own terms. And that responsibility starts with us. So I've left some references here for you. And thank you so much for listening.
Thank you very much to our speaker for that amazing presentation. Please, let's appreciate her. Let's appreciate her. Thank you very much. If you have questions, I don't know if we have any question. That was an excellent presentation. You highlight the tremendous opportunities that AI presents for healthcare, scientific innovation, and the importance of ensuring that these technologies are developed and used responsibly. I don't see any question. Okay, there's a question. The question says, what skills should future microbiologists learn to work with AI technologies? What skill should future microbiologists learn to work with?
Okay, yeah. So I think there's a lot of resources online, depending on their different tools. I would say some of the major companies that are developing tools within the AI in the life sciences include Google DeepMind, and they do a lot of teaching around how to incorporate their tools. So I would say look up Google DeepMind to start and see what resources they have on their platforms. There are platforms like Hugging Face, which is a platform where they pull together multiple AI tools in one place. And when you have access to the tool, there's also some teaching and learning that happens within the tools themselves. So I would say there's a lot of information about how to incorporate AI into your practice. It's all out there. It's just a matter of having a look, but I'm happy to send more resources after to the team, and they can forward that to you as well.
Apologies, I was muted. I said that is amazing. We would be glad to have other resources in which we will send to the participants after the workshop. We would greatly appreciate that. Thank you so much. With the absence of no more questions, we would like to appreciate our speaker once again. Please let's show us some love. Thank you, Dr. Sharon Malonza, for that amazing and excellent presentation. The message that responsible innovation must go hand in hand with equitable access and ethical governance, and also about security oversight is one certainty that we should take away from this discussion. So everything must go hand in hand. Thank you very much. I don't see our love. Please let's appreciate our speaker. Let's appreciate her. Thank you for accepting to speak. Right now, we'll be moving on to the next speaker for the day. Our next presentation focuses on one of the most important safeguards in modern biotechnology, which is DNA synthesis and screening. And the person that would be speaking on this is the person of Mr. O'Neill Hamilton. Mr. O'Neill Hamilton. O'Neill Hamilton is a leading expert in non-proliferation, disarmament, and chemical, biological, radiological, and nuclear risk reduction. He has extensive experience supporting strategic trade controls, export control systems, and counter-terrorism initiatives across Latin America, the Caribbean, Africa, Southeast Asia, and the Pacific. He has served the government of Jamaica, CARICOM, and the United Nations in various leadership roles, and has led major international capacity building efforts to strengthen implementation of the UN Security Council Resolution 1540 and prevent the misuse of CBRN materials. He currently works with the Stevenson Center Advancing Strategic Trade legislation and export controls to reduce weapons of mass destruction proliferation risk. Although he is not able to join us live, he has prepared a presentation for today's workshop, and his presentation is titled DNA Synthesis Screening as a Critical Biosafety Safeguards for Preventing Dual-Use Risk in Modern Biotechnology. I'll be taking that again. DNA synthesis screening as a critical biosecurity safeguard for preventing dual-use risk in modern biotechnology. I'll be playing his presentation. Please enjoy.
Good afternoon, ladies and gentlemen, colleagues, and distinguished members of the Nigeria Biosafe Advocacy Network. First of all, let me tender my apologies for not being with you live online. I unfortunately had another commitment emerge, which had me traveling today. But nonetheless, it's a great privilege to address this distinguished gathering on a topic that is becoming increasingly important for every country investing in biotechnology. And so I'd like to thank the organizers for inviting the International Biosecurity and Biosafety Initiative for Science, IBIS, to participate in this important discussion on emerging technologies, artificial intelligence, synthetic biology, and practical approaches to managing biological risks. So there's never been a more exciting time within biotechnology, certainly not in the modern era. Artificial intelligence is transforming scientific discovery. Synthetic biology is opening entirely new possibilities for medicine, agriculture, industrial manufacturing, and environmental protection. In Nigeria, as well as across Africa, we're witnessing growing investments in genomic surveillance, vaccine manufacturing, agricultural biotechnology, disease diagnostics, and research infrastructure. And these developments are creating tremendous opportunities. But these developments also demand that we think carefully about governance and emerging threats. Our challenge is not whether biotechnology should continue to advance. It absolutely should. Our challenge is ensuring that innovation is accompanied by safeguards that preserve public confidence while reducing opportunities for misuse. One of the most effective safeguards available today is DNA synthesis screening. a core and defining feature of IBIS's work. Let's talk a little bit about biotechnology in the digital age. Very clearly, biology, as we have known it, has fundamentally changed. For decades, scientists relied primarily on obtaining biological samples from nature. Today, biology increasingly begins with digital information. Researchers can design DNA sequences on computers. They transmit these sequences electronically to remote DNA synthesis companies. And those companies manufacture the requested DNA and deliver it to laboratories around the world. This remarkable capability has accelerated scientific research in ways that would have been unimaginable only 20 years ago. It has helped scientists respond more rapidly to infectious disease outbreaks. It has also accelerated vaccine development, enabling the rapid design, synthesis, and testing of diverse genetic sequences without relying on the physical pathogen. This capability vastly shortens the timeline for from sequencing to clinical trials. And this has also enabled new diagnostics. With all this, DNA synthesis has transformed agriculture through improved crops and livestock. It is supporting conservation efforts and environmental biotechnology. Indeed, in many respects, DNA synthesis has become an essential infrastructure for modern life science. So what are some of the opportunities for Africa? This transformation presents enormous opportunities for the continent. Many African countries are investing significantly in biotechnology. Regional centers of excellence are expanding and local vaccine manufacturing is growing. Genomic sequencing capacity has increased dramatically following the COVID-19 pandemic, and universities are producing outstanding molecular biologists and bioengineers. Artificial intelligence is also beginning to support disease surveillance, agricultural innovation, and laboratory research. So these investments are positioning Africa to become an increasingly important contributor to the global bioeconomy, and IBIS's programmatic support for the Nigeria Biosecurity Management Agency, the NDMA, is demonstrative of this. That future deserves our full and complete support. But participation in the global biotechnology ecosystem also requires confidence. Governments, investors, industry, and the public need assurance that biotechnology is being developed responsibly. Now, this is where biosecurity becomes an enabler, not an obstacle to innovation. Let's focus a bit on dual risk and what that represents. So one characteristic of biotechnology is that it is inherently dual use. The same scientific knowledge that enables beneficial discoveries can also be misused. This is not unique to biology. Artificial intelligence, chemistry, nuclear science, and cybersecurity all face similar endemic challenges. The objective is therefore not eliminating risk. That's not realistic. But the objective is managing risk realistically and intelligently. So responsible governance allows beneficial research to flourish, which is a core theme in IBIS's mission, while also reducing opportunities for misuse. This balance is the foundation of sustainable scientific progress. And this leads me now to why DNA synthesis screening actually matters. So among the many biosecurity measures available today, DNA synthesis screening occupies a unique position. Every synthetic DNA order creates an opportunity to verify that the requested sequence and the customer appear consistent with legitimate scientific activity. Most commercial providers already perform some level of screening. They compare requested DNA sequences against databases associated with pathogens or toxins of concern. They also examine customer information to confirm that the purchaser is a legitimate researcher or institution. If concerns arise, additional review takes place before synthesis proceeds. And so importantly, this process occurs before potentially hazardous genetic material is manufactured. And that makes DNA synthesis screening one of the few preventive, I'm underscoring again, preventive biosecurity measures available anywhere in the biotechnology life cycle. What about improving screening capability? How does that work in the whole spectrum of focal concerns here? So the biotechnology landscape is evolving rapidly. That is without question. Artificial intelligence can now assist researchers in designing entirely new biological molecules. Synthetic biology enables increasingly sophisticated bioengineering, and DNA synthesis screening is becoming faster and more affordable. Therefore, traditional screening approaches, while valuable, must evolve to keep pace. Future systems must be capable of identifying not only known pathogen sequences, but also novel biological designs that may present concern. They must remain effective even when DNA orders are fragmented across multiple suppliers. They must be scientifically robust while avoiding unnecessary burdens on legitimate research. And all of this, of course, requires continuous innovation. So where does IBIS fit in all of this as an entity, as an institution? For all the reasons that we have noted above, this is precisely why IBIS was established. IBIS is an independent international organization dedicated to strengthening global biosecurity while enabling responsible scientific innovation. Our philosophy is straightforward. Scientific progress and biosecurity are complementary objectives. Strong safeguards increase public confidence, and then greater confidence supports stronger scientific ecosystems. Rather than developing restrictive approaches, IBIS focuses on practical, technically credible, internationally accessible solutions, which leads me to IBIS's common mechanism. The common mechanism is our flagship initiative. It is the cornerstone and the centerpiece of everything we do here at IBIS. The common mechanism is designed to make high-quality DNA synthesis screening available across the global biotechnology community. Instead of requiring every DNA synthesis provider to independently develop sophisticated screening infrastructure, the common mechanism provides shared technical capabilities that providers can access free of cost. This approach improves consistency and strengthens security. Most importantly, it helps ensure that providers of different levels, including those operating in emerging biotechnology markets, can access world-class screening capabilities. This is particularly relevant for regions where biotechnology capacity is expanding rapidly. And so let me also update that IBIS has also made some recent additional investments to improve the common mechanism's overall operational utility. And these investments will continue into the future. Let's discuss now why biosecurity standards matter for Nigeria and also for Africa on a whole. So Africa's biotechnology future should not depend upon expensive proprietary security infrastructure available only to a handful of countries. Effective biosecurity should be continentally accessible. It must be tenable, most importantly, in sub-Saharan Africa. As African biotechnology ecosystems continue to grow, laboratories, research institutions, governments, and commercial providers should have access to the same high-quality screening capabilities available anywhere else in the world. IBIS believes that international biosecurity should be collaborative. We believe that knowledge should be shared and that standards should be harmonized. We also believe that technical assistance should be accessible and that capacity building should be targeted, meaningful, and continuous. Without question, this is the only approach that benefits everyone. Let's look beyond the technological landscape as it presents itself. Within this age of limitless possibility, we have been led to believe that technology is the omnibus antidote to solving biosecurity challenges. However, it is important to note that strong governance also depends upon people. Researchers require education in responsible science. Governments require effective regulatory frameworks, and industry requires practical guidance, and international organizations as well, of course, require trusted technical partners. This is why IBIS works, excuse me, across all these communities, because biosecurity succeeds only when responsibility is shared and shared broadly. Let's focus a bit on the critical role of international collaboration. Now, no country can address these challenges alone. Any progress will have to be predicated on a collaborative process. And we must be cognizant that DNA orders cross borders each and every day, and as such, scientific collaboration must be international. And so, given the reality that artificial intelligence is globally accessible and that pathogens do not recognize national boundaries or require passports, international cooperation is therefore very essential. As we all know, the Biological Weapons Convention provides an important international framework for preventing the misuse of biology. DNA synthesis screening, additionally, represents a core and practical contribution to the framework and towards achieving the convention's objectives, while also supporting peaceful scientific cooperation under Article 10 of the convention. IBIS therefore remains committed to working alongside governments, regional organizations, industry, academia, and international partners to strengthen these efforts. So, what is next on the horizon? The future of biotechnology is extraordinarily promising. Artificial intelligence will continue to accelerate, if not turbocharge, new discovery. Synthetic biology will continue to transform medicine and agriculture, and Africa will play an increasingly important role in this global scientific community. Consistent, though, with IBIS's mantra, our responsibility is to ensure that governance evolves alongside innovation. DNA synthesis screening represents one practical, scalable, internationally collaborative safeguard that helps achieve this objective. It is not about limiting science, it's about protecting science. So, allow me, ladies and gentlemen, to conclude with 4 key observations. First, biotechnology represents one of the greatest opportunities for sustainable development, public health, agriculture, and economic growth. Secondly, the responsible governance of biotechnology is essential to realizing these benefits. Third, DNA synthesis screening has become one of the most effective preventative biosecurity measures available in modern biotechnology. And finally, no organization or nation can build this future alone. This effort, ladies and gentlemen, colleagues, has to be totally collaborative. IBIS was created because international cooperation is fundamental and essential. Let me reiterate, we stand ready to work with governments, researchers, industry, and regional organizations across Africa to strengthen responsible science, to enhance biosecurity, and ensure that biotechnology continues to improve African lives for generations to come. And before I conclude, my apologies for sitting on the literal air overpass going into Geneva Airport, because I'm sure you may have heard aircraft flying by. But again, thank you, and I'm really delighted to have been a part of this forum, even if I were not present physically. Thank you very much, and wishing you great success for the remainder of the forum. Thanks again.
That was a beautiful presentation. We appreciate O'Neill. Please let's appreciate him. Let's show him some love. Thank you very much, O'Neill, for that presentation. You highlighted to us that DNA synthesis is one of the preventive ways to strengthen global biosecurity. And it has been proven that it is very, very supportive, and it helps to promote responsible scientific advancement. You also did mention that biosecurity succeeds only when responsibility is shared. And also, most importantly, pathogens do not respect borders. Pathogens do not respect borders. They can move around without requiring any passport whatsoever. So that was a beautiful presentation. Let's appreciate him once again. Thank you very much, O'Neill, for that beautiful presentation. Moving on now, we are going to move on to our next speaker, who would, in the person of Mr. Onyeka Nwosu, and I'll be reading his biography briefly. Onyeka Nwosu is a seasoned biological scientist with many years' experience in the areas of biosafety and biosecurity. Onyeka works with the National Biosafety Management Agency, Nigeria, and currently serves as the technical advisor to the Director General CEO of the agency. Onyeka is also currently serving as the president of African Society for Synthetic Biology. Onyeka has greatly contributed to the development of biosafety systems in Nigeria in line with the Cathycia Protocol on Biosafety, particularly in areas of policy development, safety assessment, risk management, compliance monitoring, advocacy, among others. With his vast experience in the area of biosecurity, Onyeka played a significant role in the development of the Nigerian National Biosecurity Policy and the Action Plans. He is currently a member of the Convention on Biological Diversity Advisory Group on Technical and Scientific Cooperation, as well as the ADHOC Technical Experts Group on Synthetic Biology. And please, presentation will be on synthetic biology, innovation, and biosecurity challenges, balancing scientific advancement and responsible governance. Synthetic biology, innovation, and biosecurity challenges, balancing scientific advancement with responsible governance. Join me in welcoming Mr. Onyeka Nwosu. Thank you very much for honoring our invitation. We are glad to have you with us. You have the floor.
Thank you so much, Faith. And thank you, speakers. Faith, can you share my slide?
All right, please give me a minute.
All right. So thank you so much. Hope I can be heard.
Yes, you can. Please go ahead.
Yeah. So thank you so much. Let me particularly thank the Biosafe Advocacy Network for the opportunity. It has been a very interesting presentations from yesterday and today. And I want to say that the last two presentations has also laid the ground for my presentation, which will make it more easier and simpler and faster. As Dr. Moreto mentioned of the issues of AI in life sciences, and Oniel in his presentation tried to explain and explain DNA synthesis screening are part of issues for balancing scientific advancement. So for me today, I will briefly go through synthetic biology innovation and biosecurity challenges, balancing scientific advancement with responsible governance. Next. So I want to start with the key messages for this brief presentation so that it will stick. First, synthetic biology is fundamentally changing biological capability. That is one thing we should understand. Then the second is that biosecurity risk increasingly arise from technological convergence as seen in issue of synthetic biology rather than pathogen alone. And thirdly, responsible governance requires integrating science, ethics, policy, security, and international cooperation. And finally, synthetic biology innovation and biosecurity should be viewed as mutually reinforcing, not competing objectives. So I want us to understand these key messages that it will drive us through this presentation. Now, let's agree with this quote by Fischer that science has no country because knowledge belongs to humanity and it is the touch which illuminates the world. So when we understand that science has no country, that means science has no boundaries. I therefore put it to say that while synthetic biology promises revolutionary solutions, that is synthetic biology as a science promises to revolutionize our global challenges, it also raises unprecedented biosafety, biosecurity, ethical, and governance issues. Next. So you can see that synthetic biology as a science also raises issues. It helps to revolutionize our global challenges, but it has also raises issues as regards biosecurity threats and the risk involved. And what are the innovations that are involved in this synthetic biology? You can now imagine that currently DNA strands are being transformed into digital codes. Our DNA sequences are now transformed into digital codes. You now have your ATGC binary codes. And also, global community are interconnected by the data networks. So the question is, what then happens when biology becomes data and data becomes power? What then happens, which is what is currently happening now. Most of our genetic sequences are now becoming normal data, are now becoming digital data. And the world is now interconnected with digital data. And when this digital data becomes the power that revolutionizes the biotechnology system, what happens? What will happen is that there will be a need to balance this innovation by ensuring biosafety and biosecurity and by building responsible governance. If this balance is not there, if this biosafety and biosecurity is not there, if responsible governance is not there, that means our digital goods can overpower us as a nation or as a global community. So there is a need for this balance to come in. Next. So having understood what this innovation in biology is saying, please go back. So having understood what this innovation is saying, how does this innovation apply to synthetic biology? Today, genes can be downloaded, genes can be edited, and then they can be synthesized and then further redesigned without accessing the physical biological material. That is digital biology. That is digital biology in action. And that is what is currently happening. With our sequenced gene sequences that are stored digitally, we can be able to download these gene sequences, edit it, and synthesize them, and then redesign them into the biological system we want without accessing the normal traditional biological system we know, which is having the physical biological material that we use in your lab and start your process and sequence and get your genes and start the process. But now you can do that from a digital coding that you have. And it possesses quite good intentions. It possesses quite good advantages that help to solve our issues, such as it can help us in disease surveillance and vaccine design. It can help in crop improvement and conservation genetics, and it can help us to start developing synthetic biomaterials. But the question is, should genetic data be treated like physical resources? It's a question we should answer within ourselves as we go further to X-ray discourse. Next slide. So, what is synthetic biology in its entirety? In line with the Convention on Biological Diversity, which is the current international body discussing the issues of synthetic biology, it defines synthetic biology as a further development and new dimension of modern biotechnology that combines science, technology, and engineering to facilitate and accelerate the understanding, the design, the redesign, the manufacture, and or modification. So synthetic biology does not only mean to manufacture a using through de novo synthesis. That is completely from what you can synthesize from your genetic code, you will completely manufacture a new gene. That is not only where synthetic biology stops. But synthetic biology, you can use it to redesign what is already existing. By understanding the sequence of what a biological system that is already existing, you can redesign into something else. Or you can modify a genetic material that is already existing. That is, you can modify through synthetic biology, you can modify the genetic material, you can modify living organisms or a complete biological systems. So synthetic biology extends beyond traditional genetic modification. You know our normal genetic modification, we know that leads to our normal genetic GMOs, genetically modified organisms. But now synthetic biology, which is a new trending emerging biology, is now extending beyond the normal traditional knowledge of genetic engineering we know. So it is now using technologies and tools that we aid them to achieve their aim. And such of these tools are artificial intelligence, machine learning, or digital sequence information, which we call DSI. So they now incorporate these tools to help in de novo synthesis. De novo synthesis means completely synthesizing a new biological material, completely new synthesis from what it is being known in vitro. So this is the way synthetic biology has extended. Next slide. So having clearly explained what this synthetic biology is, and I mentioned that it now applies or adopts AI and digital sequence information, which is DSI, to operate. I now ask, what is this digital sequence information and why does it matter whenever we talk about synthetic biology? Digital sequence information refers to the genetic sequence data stored digitally. So all our genetic sequence data that are stored digitally, we refer to them as digital sequence information. And what do they offer? They include DNA and RNA sequences. They include our protein sequences. They include all the bioinformatics data sets. And they also include all the metadata linked to organisms. So these are what digital genetic sequence information are. And so far, they are genetic sequences that are stored digitally. It becomes a very crucial genetic material that are highly used in synthetic biology. Next slide. Next slide, please. So, where does AI now converge with genetic digital sequence information? which we have mentioned earlier, the involvement of AI in life sciences. And now I am mentioning that when AI now converge with this digital sequence information, a complete digital biology happens. So the conversion of AI and digital sequence information is creating what we currently call digital biology, where large DSI databases like our gene bank are completely analyzed by several AI algorithms, and we now use this to make breakthroughs. For instance, AI can read a vast DSI dataset. That is, AI can be used to read a vast digital sequence information, and we can use it to identify new gene that functions or can be used to design a novel protein that have never existed in nature. This will help us to bridge the gap between raw genetic data and functional applied technology. So you can see the power when AI converge with digital sequence information. It will completely give us the digital biology that is now used for synthetic biology. Next slide. So having understood what digital sequence information is, and understanding that when digital sequence information converges with AI, it gives us a powerful tool of digital biology. We are now saying, when this DSI combines with AI, and this AI combines with the explanation of synthetic biology that I've said, what will it give us? Truly, it's going to give us a new bioeconomic innovation. Normally, as I said before, our traditional biology is what we normally know is from collecting our organism and then go to the lab and do our normal study, do our DNA synthesis and so. But now, what is now, when these three converge together, it now brings up what we call modern biology, where you now download the sequence, the digital biology, and then design it digitally using your AI powerful tools, and you can use it to build new biological systems. And from different applications of synthetic biology, it has been adopted in developing mRNA vaccines, engineered bacteria for medicine or for agriculture. It has been adopted, research are going on where it's being used for biofuels, for climate smart agriculture, and synthetic enzymes for industry. So this thing has helped critically for protein structure prediction, enzyme engineering, metabolic pathway optimization, gene circuit design, and a lot of automated laboratory pathways. When these things are applied, you can use it to get all these vaccines, mRNA vaccines that have been used. That is synthetic biology. And truly, this convergence has given us a new bioeconomic innovation that tends to solve most of our global challenges. Next slide. So, having explained this synthetic biology, how AI converges with it, the question is, why are we discussing it? Why is it now a matter that should be discussed? Synthetic biology, yes, is redefining our ability to engineer living systems through increasingly accessible and programmable biological technologies. This same innovation can enable us for pandemic preparedness, precision medicine, sustainable agriculture, climate solutions, but also it can increase concerns regarding areas like deliberate misuse, accidental release, AI-enabled biological design, supply chain vulnerabilities, and the emerging biotechnology, emerging biosecurity threats. So you can see that it has the capacity as a bioeconomic innovation to solve our global challenges in the areas of agriculture, health, environment, sustainability. But at the same time, it raises a lot of concerns in areas of misuse, both deliberate and accidental, supply chain vulnerabilities, and a lot of biosecurity threats. So by this explanation, you can now confirm and affirm that synthetic biology innovation is a typical example of a dual-use science. And because it is a dual-use science, That is why this discussion we are having today matters. Next slide. So, all through yesterday, we have been mentioning what dual-use research concern is. And here, I just want to reemphasize that synthetic biology research intended for beneficial purposes may also increase pathogen virulence, expand host range, improve environmental persistence, enhance transmissibility, evade diagnostics, and circumvent existing therapeutics. So, in as much as it is beneficial, it may also cause all these concerns. So, these great new governance challenges, for the fact that it's not, there are risks that raises concerns, which we have referred to as a dual-use science. It means that there will be a new governance challenge from what we already know before. Our normal genetic engineering, our normal modern biotechnology processes, we already have some governance systems that are already governing them. But now we are seeing a new system that is converging AI and digital sequence information to give us beneficial purposes, but at the same time causing some concerns. It means that it will also create a new governance challenge beyond our traditional biosafety framework that we know. Our normal traditional biosafety framework handles our modern biotechnology like GMOs and so. But now we are seeing a new innovation. It means that since there is a new innovation, there will also be a challenge in already existing governance structure, which is our traditional biosafety system. And therefore, this brings us more focus to biosecurity relevance. Where does biosecurity this is where biosecurity becomes relevant in addressing issues of synthetic biology as a dual-use science. Next slide. So, synthetic biology innovation is now changing our biosecurity landscape. How? Historically, what we usually do is that we assess any access to dangerous capability will require us having high containment laboratories. It will require us having specialized expertise. It will require us having significant financial resources. You will agree with me. This is what we normally know, the historical aspect we have in how to assess dangerous capabilities of pathogens. What we usually have is you set up your high containment lab, special expertise, and you have the significant financial resources to manage it. But today, with what we are seeing as synthetic biology that brings a lot of bioeconomic innovations, the capabilities are increasing, and they are increasingly democratized through commercial DNA synthesis. Now you can commercialize because of it. You can download, you can sequence online. That means for now you can have commercial DNA synthesis. That means I can order a DNA sequence from any commercial distributor. You can now have open genomic databases. So all these things are in the open because they are digital biology. You can now have AI assisting in designing these new organisms. We now have cloud laboratories. That means you go into the cloud system and take the sequences you want instead of normal physical laboratories we do. The issues of automation are there, and now international collaborations has come up. Therefore, what we are having today has shown that biosecurity must evolve from controlling pathogens to governing biological capabilities. Next slide. So, where does biosecurity have relevance? So there are a lot of innovations that help to aid synthetic biology, like CRISPR technology, which you know. CRISPR helps us, which we apply in genome editing. It helps us for precision editing. But where does biosecurity come in? The relevance of biosecurity is that in this case, you will easily modify pathogen. So if it is a high pathogenic organism, you can use CRISPR technology that supports synthetic biology to easily modify pathogen. So for you to easily modify pathogen, biosecurity relevance comes in. Biosecurity has to look at it. You also have DNA synthesis as part of synthetic biology process. In this case, you will rapidly construct, you will rapidly have a construct generation. So you can synthesize your gene rapidly. So what is the biosecurity relevance? Potential reconstruction of pathogen. it means that a high pathogenic organism can also be reconstructed using DNA synthesis. So we have AI protein design that also helps synthetic biology. The scientific value in it is that it helps us for novel therapeutics, like in the issues of vaccine. But the question is, the biosecurity relevance is, it can also be used to design harmful proteins. We have our gene drives, which helps us in vector control. Today, we are now talking of GM mosquitoes, which will help us to reduce our Anopheles vector mosquitoes and therefore reduce malaria, which is a very powerful and innovative technology. But in its the relevance of biosecurity here is that it has some ecological consequences because most of these gene drive technologies are irreversible. Then you have your synthetic genomes, which is now the vaccine platforms that are being used. But the biosecurity relevance there is that it can help to create novel organisms and so on and forth. So you can see that there are synthetic biology innovations that have very high scientific values, but at the same time, there are biosecurity relevance that is of concern. Next slide. So what is, having understood all these things, what are the biosecurity risk pathways? So you have your innovation, which we have explained here, the synthetic biology innovations. When there is this innovation, you can now use this innovation to generate knowledge, meaning that people will now have access to this technology innovation. They will now have knowledge about how this technology or synthetic biology innovation comes to play. And when they now have this knowledge, they will now be able to disseminate it. They will now be able to pass this innovation through. And when they pass this innovation through, it means that we are expanding the capability of many people having this knowledge of this innovation. And when many people start having this knowledge, this innovation knowledge, potential misuse will start playing because people that has malicious intent will start gathering this knowledge. And when malicious misuse starts coming in, we will now start having serious biological incidents. And when we start having these serious biological incidents and threats, it will now lead to several public health, economic, and national security consequences. So in all these pathways, you will see that there's an inside threat, there's an insider threat, there is a state actor, there is a non-state actor, because during technological innovation process, those involved, the insiders there, can serve as insider threats who can take this knowledge and give to people that are not supposed to have this knowledge. Even the state actors, when it is even an innovation that is formally or responsibly approved to take place, state actors can also find a way to misuse it because they are in possession of it, and so on. So you will see that all these people are involved in this biorisk pathway. Now, having understood there's a biorisk pathway for synthetic biology innovation, how do we balance it? So we must balance synthetic biology with security. And balancing synthetic biology with innovation and security, it simply shows that innovation alone is insufficient. So synthetic biology innovation alone is not sufficient. And security in itself, if you handle security alone, it may stifle innovation. So if you bring in security as a barrier, no, don't do this. Security, we have stopped this process, we have stopped this innovation. If you bring it and consider it alone, you will see that it will stifle our innovation, it will stifle our scientific discovery. Therefore, there must be a balance. And where does this balance come in? Risk assessment, effective risk assessment must come into play. We must bring in ethical process into synthetic biology process. And very important, we must set up a governance system that will be able to regulate synthetic biology innovative processes. And then public engagement. Public must understand from the onset of the innovation and to its commercialization, so that you will be able to balance synthetic biology and security. Therefore, balancing the effectiveness and the importance and the need of synthetic biology solving our global challenges. So currently, there are regulatory gaps in this area of synthetic biology innovation, which include that rapid innovation outpaces legislation. We agree with me that the rate at which bio innovation, such as synthetic biology innovation is coming, it is outpacing our legislation. Now we are talking of DSI, digital sequence information, where all our genetic sequences can be stored digitally. And when it's stored digitally, it crosses borders. This one has outspaced transboundary movement, where we can use our border control to checkmate biological materials coming. But with the issue of DSI, it has transbound boundaries. We now have AI-generated biological design. It has now promoted do-it-yourself biology, where community, everybody can gather and do it yourself, even with your laptop systems. We now have international regulations that are inconsistent, because we have an international regulation that handles the physical biological materials. Now we are seeing DSI issues, and now there is inconsistency on how to regulate these together. And the verification mechanisms. Please go back to the slide. So we are now having verification mechanisms under our biological weapons convention that remains limited. So what we are saying is that responsible governance framework must provide governance to these regulatory challenges by researchers having scientific responsibility, and our institutions doing this research providing institutional oversight. Why governments as a nation will provide national regulations that will guide institutions and researchers, whereas international corporations, such as organizations like BWC, CBD, and so on, will now provide the international cooperation that will guide the global norms for us to provide governance for synthetic biology innovation. And all these, we have components that relate to risk-benefit assessment. You should be able to do dual-use research consign reviews. You should be able to do our ethical reviews. And most importantly, which O'Neill mentioned, we must be able to do DNA synthesis screening. Screening remains an important aspect of synthetic biology, and we now have issues of cyber biosecurity, responsible publication, and secure data. But please, next slide as I round up. So I wouldn't go further to mention issues of DNA synthesis screening, which O'Neill has mentioned, but O'Neill has emphatically mentioned that DNA synthesis is a biosecurity tool that can handle synthetic biology innovation, where we should be able to know who is doing the sequence, who is ordering the sequence, is the person has the capable to commercialize this sequence, what is he using the sequence he wants to procure to do. It is very important in this system. Next slide. So what are the policy priorities for government? I'm able to divide it in terms of policy. We should be able to develop and strengthen our national synthetic biology strategies. We should be able to update our biosafety laws, so that about our biosafety laws, for it to include synthetic biology, DNA synthesis screening, include cyber security. I can tell you that Nigeria's biosafety law as at now has recognized the regulation of synthetic biology. And Nigerian biosafety law Nigeria is the first in entire Africa to remodel or amend their biosafety law to include the regulation of synthetic biology. And we must have to integrate AI governance into our biotechnology regulation. For institutions, we need to strengthen our biosafety regulators, build efficient bioethics committee, improve workforce. And for international diplomacy, governments must involve in international bodies discussing these issues and must support international confidence building education. Next slide. So let me just give you a case study from what we have done. In case of a de novo virus synthesis, what do you think will happen? Scientists have demonstrated the ability to synthesize virus from a published genetic sequence. So from what has been published, they were able to synthesize a virus de novo, completely have a new synthesis. So what are the lessons that you learn from such a case study? Please, next slide. So the lessons we learn from this case study is that there is a high need for us to start doing sequence screening, for us to have synthetic biology research oversight, for us to input into our governance system what we call responsible publication. Not everything must be published. And then there should be international cooperation to guide this, so that whatever the way it's being done in US will be the way we also do it in Nigeria. Next slide. So what are the future directions? The future emerging biotechnologies that are linked to synthetic biology, such as AI design organism, will start coming up. These are the future direction. We have issues of xenobiology coming up, and these new emerging technologies are coming up. It will reshape our biosecurity further. And therefore, I ask this question: can regulation move as fast as biotechnology? It is left for us to answer. But what I'm here to say is that future governance must become predictive, it must become adaptive, it must become international, technology neutral, and risk informed. So I just brought this slide, and I want to ask, what if we want to set up a team, a football team, that will be able to look into synthetic biology innovation in the country as a system? Who do you think will make the first 11 in this team? And I brought this slide for you to see that government becomes the keeper. Government is the keeper that will keep all the processes by providing the necessary regulations. And you will have your defenders, which are your regulatory authorities, the laboratory facilities, the biosafety and biosecurity officers. And then you will have your midfielders as the scientists who do this research, and you have your vet officers who should be able to be on ground to understand this impact on animal. And then going further, you will see what I wrote there. I intentionally blocked this slide to let you know that biosafety and biosecurity remains a critical importance in synthetic biology innovation governance. Next slide. I now return back this key message that I mentioned before. So I intentionally brought it out for you to see that I have eventually been able to extract these key messages from the beginning, and we're able to see it here. Next slide. So in conclusion, synthetic biology represents one of the defining technologies of the 21st century. Its capacity to accelerate innovation in health, agriculture, and environmental sustainability is unprecedented. However, the same technological advance also expanded the spectrum of biosecurity risk from deliberate misuse and insider threat to AI-enabled biological design and cyber biosecurity vulnerabilities. So we must build a resilient governance system that will require adaptive regulation, responsible research practices, robust biorisk management systems, international cooperation, and continuous engagement between scientists, security experts, policymakers, industry, and the public. It is only this way we can be able to bring balance between synthetic biology innovation and our biosecurity challenges. Thank you so much for listening.
Thank you very much, Onyeka, for that well-detailed explanation. And that was a lecture, apparently. It was a very beautiful one. Thank you very much. Yes, please, let's appreciate our speaker. Let's appreciate our speaker. That was a beautiful presentation. That was a well-detailed presentation. And I just want to let you know that these presentations will be made available. The resource material will be made available to all registered participants. Thank you so much. And our final technical presentation for today is which will further expand our knowledge on synthetic biology from both the scientific and the biosecurity perspective in the person of Mr. Yogo El Mubarak. So Yogo is a synthetic biology and biosecurity specialist whose work spans research, education, and community engagement with a focus on responsible innovation and science policy linkages. He previously served as a coordinator at the iGEM Foundation, home to the world's largest synthetic biology innovation competition, and was recognized in 2021 iGEM Safety and Security Fellow. Since 2023, he has collaborated with the United Nations Office for Disarmament Affairs across both the Youth for Biosecurity and Youth for Disarmament initiatives. It was recognized as the 2025 GAP Summit and 2026 Excellentium Leaders of Tomorrow. He served as a technical consultant for the International Biosecurity and Biosafety Initiative for Science, contributing to the common mechanism and the global DNA synthesis map. His technical background spans AI and biolab automation, biomedicine production, and structure-guided drug design. Today, he will present on synthetic biology design and engineering, emerging research application, technical challenges, and biosecurity consideration. Please join me in welcoming Yogo. Thank you so much, Yogo, for honoring our invitation. You now have the floor.
Thank you, Faith. Hi, everyone. Thank you for having me, for the network, for the speakers, for the participants, for being so patient and for making it this far in the workshop. I'm very much aware that I stand between you and a very exciting hands-on exercise and a very well-deserved rest. So rest assured, I won't consume the 20 minutes because all of the previous amazing speakers, they spoke in depth about synthetic biology, responsible innovation, the different lenses and the way in which you can look at this field specifically. So throughout this segment, I'll briefly just share with you some more like specific examples based off previous work that I've done and also some existing work in the field that will hopefully give you an idea of applications related to synthetic biology and where does biosecurity also sit and impacts the field as well. So I'm sharing the screen. You can see the screen, right? Okay, perfect. Yeah, so throughout the presentation, you'll see that I will echo most of what the previous speaker said and many of the speakers today said. So hopefully this will be like a summary for you. Starting off with some of the fundamental questions of synthetic biology. So how the field initially started and some of the questions that really shaped of what we look at synthetic biology today. So almost 20 to 25 years ago, there was a fundamental question that was asked, can we actually build synthetic life or apply the concepts of programming and computer to biological systems? And 20 years later, it turns out that yes, it can be done, but there are obviously a lot of challenges before we get to fully mature technology. So in a way, synthetic biology, although it's been around for quite some time, it's still an emerging technology. I'll spare you like another definition because I feel like you've heard enough about it already. But in a way, you can keep in mind these four fundamental questions that really shape the field. So can we actually create synthetic life? Should we equate living things to their functions? Does being alive necessarily imply being in physical form? And is life more than the sum of its parts? So hopefully what you see on this slide would help you answer these questions when you think about synthetic biology. So for example, for the first question, the way that synthetic biology helped explore this question is that it created new systems or new biological systems that might not exist in nature, or it helped re-engineer existing functions for different purposes to enhance life, to augment life, or to really shape the way that we do things and we use technologies all around us. So going back in history, obviously, if you're a life scientist, hopefully you've heard about some of these big milestones. So we talked about DNA synthesis, DNA screening. We talked about a lot of these different milestones, and it all started with when we discovered the structure of the DNA, right? So the double helix is really what shaped most of the knowledge that we know today. So fast forward to 2004, so that's when one of the first synthetic biology conferences was hosted, and IGEM, which was the group that I worked with in the past, really started to emerge as an organization that really fosters the next generation of bioengineers who will hopefully lead the field in the future. After 2021, so with the development of AlphaFold, there was a lot of impact that happened in the field as well, specifically in structure-guided drug design and the way that we access information when it comes to structure resolution for proteins and drug development. So in a way, everything that you've heard in day one, day two can really fit into these four major categories when you think about synthetic biology and the application spectrum. So most of the applications fall under enhancement. So enhancing an organism's existing functionality, for example, increasing photosynthetic capacity for algae or other plants. Another category is augmentation. So augmenting an organism with another function or combining existing ones that are already in nature. A third category is function creation. So creating an entirely new function and an organism that doesn't already exist in nature. And the last one, creating whole organisms. So we've seen in the past some of the most exciting innovations in the field were creating basic whole organisms, mostly bacterial organisms. So in a way, when you think about synthetic biology and the application spectrum, this really falls under these four major categories. Obviously, like what was said before, synthetic biology is an emerging technology or an emerging field, and it has several challenges. Biosecurity is one of them, but it also has a lot of technical, economic, and consumer challenges. So some of these, you see them on the slide, but I'll take one example. For instance, if you're in the field, you've definitely came across scale up. So how do we actually scale up these many proof of concepts that we see in synthetic biology, and how can we actually take them to production and create impactful commercial products that will change the way that society works with, for example, therapeutics or space exploration. So that's obviously always a challenge. It was already a challenge, but in synthetic biology, it's an even bigger challenge if we want to think about how to scale up these technologies and the proof of concepts that we are working on. The specifics, so just zooming in on biosecurity, and that's why you've spent 2 days listening to the wide variety of speakers talking about responsible innovation in the life sciences, biosecurity. So biosecurity is obviously one of the most important challenges. I'll spare you another definition as well, but I'll go into how biosecurity expanded its scope throughout the years. So it initially started as focusing on the threat of biological weapons, and specifically in the hands of state actors. So focusing on their prohibition, on proliferation and disarmament. So in the past, several states have developed bioweapons for offensive reasons. Then, as the nature of conflict evolved, biosecurity broadened to encompass prevention of bioterrorism. So the barrier of entry or knowledge became lower, and non-state actors had access to such technologies to do harm with it. And today, it's more concerned with broadly protecting people and society from biological threats, regardless of their source, whether it's intentional, accidental. And yeah, so the spectrum of potential misusers in biosecurity also changed together with the traditional institutional enforcement. So initially, global biosecurity has focused on state actors, then state developed scientific and material capabilities to construct, package, and deploy biological weapons. And then the pursuit of bioweapons has extended to non-state actors. I'll spare you some of the examples, but some of them you see them already on the slide, and there's a lot of documentation that would definitely be interesting for you to explore. In a way, as a researcher, so we're all here, we want to do good, we want to improve our societies, we want to see a better future for humankind. And in a way, this really is summarized in a few circles whenever you're conducting any type of research. So it all starts with you and your team. So you're doing X type of research. Hopefully, that's why we are here, and that's why we spread awareness about these topics. We try to push researchers to think about these different circles that their research eventually will impact. So the people and animals that are involved in the project, a broader circle, so the stakeholders and other community members that are involved and are impacted by your project, once you deploy your project and the environment and the society, and of course, thinking about the implications of that project that you're working on or the research for the long-term future. So just sharing with you a practical examples of how specific communities think about these topics. So like the circle of concerns, oversight of the innovation that happens within these communities. So I'm taking iGEM as an example because that's where I spent the past 5 years of my professional career thinking about synthetic biology and these specific questions. So if you're not familiar with iGEM, iGEM is a collective that started almost 22 years ago with this fundamental question. So can you actually apply computer science topics or concepts to engineer life? And now iGEM is regarded as the heart of synthetic biology. So in a way, a lot of proof of concepts are emerging from iGEM. A lot of synthetic parts are created throughout different programs. And to give you an idea, the flagship program, or in a nutshell, iGEM is a combination of 6 programs. And the flagship program is the competition. So that's where we host students and industry individuals from different parts of the world, so for more than 60 countries. They build teams, they use synthetic biology as a tool to develop solutions and proof of concepts to common challenges that we see around us. So space exploration, therapeutics, climate change, so on and so forth. So through that competition, as teams are using synthetic biology, they are also brought to think about the implications of their projects on the society and the implications of the society on their projects. So it's a two-way street for them to think about and be involved in this proactive thinking about responsibility and the implications of their project. So obviously there's a governance structure within the iGEM ecosystem. So it all starts with the Safety and Security Committee, which oversees most of these activities that happen within iGEM and the competition. And this committee involves stakeholders from different fields and different international organizations to think collectively about some of these risks that might arise from the competition projects, but also to educate iGEMers. So in a way to help them think, so let them be the ones who are thinking about the risks, and we're not actually dictating for them how they should think. We only provide them with the tools. So everything that was presented over the previous couple of days, we provide them with these tools so that they can use them to think about these risks that might arise from their projects. iGEM also has like a bunch of safety policies to really help teams navigate the innovation ecosystem and to really use synthetic biology as a tool for good, and also think about the details and whether it's necessary to go down a specific path or not. So these policies involve animal use, human subject research, AMR or antimicrobial resistance, and many others. And these are all overseen and developed by the Safety and Security Committee. Of course, there's a lot of focus on the risks, but through biosecurity, there's a lot of opportunities for teams to also innovate through the competition. So we've seen teams innovate at the level of biocontainment, so how they can track and control organisms that might leave the lab, both deliberately or accidentally, keeping in mind that in the scope of the competition, teams are not allowed to release anything. But they do spend a lot of time thinking about what could we do, what kind of biocontainment strategies we can develop to really contain any type of release. They also think about safe by design. So they address safety and security concerns early in the development process. So they really integrated earlier in that process and not just like as an afterthought. And they also think about how can they adapt to the new technologies. So there was an example that was mentioned on cell-free systems, which is an exciting new technology. So it basically takes out the technical machinery of a cell that produces proteins and uses DNA as a structure, but it takes out this living system aspect. So it's more like a chemical mix where you can produce novel proteins, where you can also produce toxins, which is also another biosecurity consideration to think about whenever you think about these new, whenever you deal with these new tools. I'll also spare you the details here, but you've heard a lot about the different advancements in synthetic biology, so such as CRISPR, the application of AlphaFold, and how it impacted the field of structure-guided drug design. But most importantly, the falling cost of DNA synthesis, which is really the first building block of any research. Whether you are in synthetic biology or just life sciences, your research starts with a customer, so you're the customer, and it starts with you ordering a piece of maybe synthetic DNA or nucleic acid. So you've heard it before. By nature, whether it's synthetic biology, whether it's nuclear sciences, whether it's chemistry, physics, by nature, these sciences are dual use. So there are a couple of really interesting examples that illustrate the dual use aspect or nature of synthetic biology, such as the de novo synthesis of the polio virus or the reconstruction of the 1918 Spanish flu influenza virus. So these are two very interesting papers that illustrate how researchers were able to achieve this, but more importantly, how they disclosed that research to the public, which is a whole other process when you think about information hazard and how much you should talk about dual use cases whenever they come up. Another interesting paper that or example that you might want to look at is the mousebox paper. So this is another aspect or case where a team of researchers were able to study the immune response of mice to a modified mousepox virus. So eventually, the researchers were able to create a modified mousepox with a 100% case fatality rate and ability to evade existing immunity from vaccination. So this also gives you like a perspective on how much you can do with synthetic biology and how much you should do with synthetic biology with everything that we have right now in terms of biosecurity countermeasures and how much we can develop in the future. You must have heard this yesterday. I recall one of the speakers mentioned something about mirror life. So in case you're not familiar with the topic, it's like an emerging topic within synthetic biology. In a nutshell, all known life is homochiral. So whether it's DNA or RNA, they are right-handed nucleotides, and proteins are made of left-handed amino acids. So a team of researchers a few years ago, they were driven by the curiosity of these kind of applications, and they decided to create. They began to work towards creating life forms composed entirely of mirror image biological molecules. So the complete opposite of what you see in nature, and such mirror organisms would definitely constitute a radical departure from known life. So in recent years, or a couple of years ago in 2024, there was a call to halt research on mirror life. So the report that you see here is far more extensive from what I'm telling you right now. And a group of researchers and specifically Nobel laureates, they called to halt this type of research. And there's a whole group of people working on hosting workshops and conferences to really think about the future of mirror life and what should we do in the next decade to really think about anticipatory governance. So one of the topics that the previous speaker also talked about. Once again, it was mentioned many times, so lower barrier of entry to dangerous actors with AI, with synthetic biology. All of these technologies combined means that more people have access to creating different types of proof of concepts. And biosecurity risk is not just focused on, it's not just like by dual use research. The ease of access to synthetic biology tools are also lower. They also lowered the barrier of entry to dangerous actors and cheap and affordable DNA synthesis tools. They may allow actors to produce decentralized DNA sequences. So that's why everything that IBIS is trying to do and some of the work that they've done on the common mechanism, on the global DNA synthesis map, just to give everyone a perspective on the market and what everyone is doing in terms of DNA synthesis is crucial, especially nowadays with the advent of the intersection of AI and synthetic biology. I'll skip the intersection of AI and synbio, but it's not 2026 if we don't talk about this intersection. But there's a wide variety of examples that were also mentioned on the opportunities, but also the risks of these kind of intersections. And just to conclude, I've added this slide here because I was fortunate enough to work on what IBIS is trying to do within the common mechanism and the global DNA synthesis map. So over here you have the specific definitions, but the IBIS website have extensive information on the common mechanism, on how it operates, on how it's being developed, where it does it stand now, and what kind of other tools exist in the ecosystem. So keep in mind that IBIS is just one of the stakeholders that are developing these kind of tools. The major difference is that IBIS is developing a free and open source tool that is intended to be provided to all DNA synthesis providers. The global DNA synthesis map is also an interesting product. It really gives you like an overview of a big majority of the key players in the market in more than 80 countries, who's producing DNA, who's shipping DNA, and how it's being shipped, and what kind of policies exist, keeping in mind that not many exist nowadays, and there's a lot of advocacy happening to put in place policies around DNA synthesis. So yeah, with that, I'll just conclude. I'll keep it brief. Thank you for listening, and hopefully you'll enjoy the workshop. So I'll see some of you in group 7.
Thank you, Hugo. Thank you so very much for that beautiful presentation. Please let's appreciate Hugo. Let's tell him thank you with our reactions. Do we have questions for Hugo? I don't see any question in the Q&A box. Okay, yes, we do have some questions. All right. This says, thank you, sir, for this wonderful presentation. I would like to ask, is there a particular AI that would be recommended to use in assessing DSI, and how to humanize and cross-check the limitations of AI that it can make a mistake? I don't know if you understand that question. I'll be taking it again. Thank you, sir, for this wonderful presentation. I would like to ask, is there a particular AI that will be recommended to use in assessing DSI, and how to humanize and cross-check the limitation of AI that it can make a mistake? Okay.
Okay, I'll definitely defer the question to the previous speaker, because I definitely acknowledge that he has far more knowledge on DSI, and I don't have like any specific examples on any AIs in that regard, but I'll definitely look it up and try to share it through the call.
All right, thank you. We also have one more question. I don't know if it's for you as well. Should some areas of synthetic biology research have stricter controls, and why?
So in a way, I don't think it's about like having stricter controls. So it really goes back to like the anticipatory governance. So a very specific example is mirror life. So the idea is to look ahead into the future and think proactively. What can we do? Like what kind of safeguards we can put in place before the technology matures enough to generate risks that we can't, that we don't have any countermeasures for. So no matter what the technology is, I think it's really about this approach that we should have about anticipatory governance, whether it's at the policy level or the technical level. And yeah, in a way, most of the work that's being done here, it's really about mitigating the risks. There will always be a risk. You can never like, let's say, eliminate the risk 100%, but you can definitely mitigate it to a certain extent. I'll definitely also defer to the other speakers if they have anything else to add, but that would be my take on this question.
All right, thank you so much. Please let's appreciate Yogo once again. That was an excellent presentation and a good conclusion to our technical sessions. And together, we believe that today's presentation have demonstrated how emerging technologies, such as artificial intelligence, DNA synthesis, and synthetic biology are reshaping life science, and how they're also important to biosafety and biosecurity. So while we are reinforcing the importance of responsible governance, biosafety, biosecurity. So thank you so much once again, Yogo, for honoring our invitation. It's so glad to see you again. All right, right now we'll be moving on to the final part of the workshop, and I would like to invite my co-moderator, Dr. Precious Ipo, to take this session. Thank you so much for staying tuned.
Thank you very much, Faith, and thank you everyone for staying to this time. We appreciate everyone. In a few moments, we will be going into our various breakout sessions, and we'll have some simulations. We have already divided every participant into 8 groups. So move into your own breakout session, which is automatically done. And we are going to have 10 minutes for discussion within your group, after which you come back and have a 2-minute presentation. It promises to be very exciting. And there's also going to be a take-home assignment that you will have to submit to the workshop thereafter. So I believe we have all moved into our breakout rooms now. Identify your breakout rooms and we'll start the scenario right away. Thank you very much. The time is 10 minutes and group presentation is 2 minutes. We have 8 groups for this workshop. Thank you. Please, if you have any problem, you can just meet those of us moderators and we'll guide you. Thank you so much. Hello. Is anybody here?
For those that have not been assigned, the stimulation exercises are just been pasted in the group, in the chat box. Please download the stimulation exercise. Also, the link to the exercise will be shared. Please download the file. The file contains the stimulation exercise. Group 1 and group 1 to group 4 will be anchoring. They will be treating scenario 1 to 4. Group 1 to group 4 will be taking scenario 1 to 4. And for those that are unassigned, we'll be assigning you now.
How could the group. Hello? Hello? Anyone there? Oh, please, assistance.
Hi everyone. Please, if you can hear me, the scenarios have been shared in the chat box. Please download the scenarios. Here is the scenario. Please download the scenario or use the link. Use this link to access the scenarios. So you can have it.
Sorry, Faith, can you reshare the link for the scenario?
I just reshared it, and I'll also be sharing it as a file. So if you were put in a wrong group that is different from what you have initially, just work with the group that you are in currently.
Okay.
If a malicious act, oh, sorry.
I sincerely apologize. Oh, we are so sorry. We are so sorry. The breakout room was cut short because some people do not have the scenarios. Apologize about that. Now the scenarios will be reshared in the chat. We had a lot of groups complaining that they don't have the scenarios. So I would like to take the instruction again, and then we'll be reshared back into our breakout rooms, our respective breakout rooms. So the scenarios are being shared now in the chat. Group 1 to 4 are to work on scenario 1, and group 5 to 8 are to work on scenario 2. Group 1 to 4 are to work on scenario 1, and group 5 to 8 are to work on scenario 2. So now we have the document in the chat box. Please download the scenarios there. You can access the scenarios there. And we also have the link if you want to use the link to access the scenarios. So this will provide you everything you need. So we are going to restart the timer, and we have 10 minutes approximately to work on them. Thank you.
Thank you.
Faith, we are restarting the timer, right?
Yes, we are.
Please, can anyone assist me how to join group 1?
So, Dr. Sharon, are we still waiting here or we have to go back to the main group or main chat?
I think we are back in the main chat now.
In about 41 seconds, we'll have others join us, and then we'll have our presentations. We've come to the end of the workshop. Thank you so much, everyone, for staying till the end. Hi, everyone. Welcome back. Welcome back. Thank you very much. I hope you had a great discussion. I hope you had a wonderful discussion. Now, can we have presentations from a representative from each group? Group 1, can we have a representative? You can use the raise hand icon. If you group 1, use the raise hand icon and we are going to call you. Group 2, raise hand icon. Group 3, group 4, group 5. Please let's have our presentations. 2 minutes. If you are representing your group. All right, Jed, what group are you representing? You can unmute and speak.
Hi, good evening, Dr. Faith. I'm gonna representing Group 2 for Biosafety for Scenario 1. And with me with Sir Siddharth to answer the other questions.
Yes.
Thank you.
Please go ahead.
Okay, we're going to ahead. So, good evening to everyone. We are Group 2 regarding the biosafety, and we have this scenario. So I'm not gonna read the whole scenario. It's about engineering a highly transmissible influenza virus. First question: what is the main dual use concern? Firstly, avian influenza is highly transmissible. So the researchers, based on the scenario, is determining the genetic composition of the avian influenza virus for the purpose of determining its pathogenicity for pandemic preparedness. So the main dual use concern is the genetic mapping of the avian influenza. Then second question, what are the potential public health benefits? Firstly, if we would like to map the genetic composition of the avian influenza, we can determine its pathogenicity, transmission rates from person to person, so that we can apply what kind of biosafety measures we can prepare in case of a pandemic or a surge of avian influenza disease. So for the questions 3, 4, 5, I would like to call Sir Siddharth to answer the question. Thank you.
Yeah, on question, can you unmute me? Can you hear me?
Yeah, I'm muted. Please go ahead.
So on question 3, what biosafety and biosecurity measures are required? So we would do a risk assessment before the project begins, and whenever there's a change in protocol, whenever we are adhering to the certain standards, then we'll appropriate containment which is matched with the avian influenza and the procedure in dealing with handling the highly pathogenic avian influenza viruses. And we'll also have trained and competency assessed personnel And we'll also have appropriate personal protective equipment, and there will also be regular emergency response planning and incident reporting, and independent institutional biosafety oversight. In biosecurity measures, we would take the accountability of the pathogen stocks, controlled access to pathogens and sensitive information, secure storage and transport, and institutional review of research with dual use, and of course compliance with the national regulations and international guidance. To the fourth question, how can risk be reduced while preserving the scientific value? So we will prioritize surveillance, diagnostics, vaccine development, epidemiology, and antiviral resistance studies. Then we'll use non-infectious experimental systems or attenuated models when they adequately answer the user questions, and conduct independent risk benefit assessment throughout the project. And we'll also, coming to the last question, should the research proceed unchanged? Generally, no, because research involves highly pathogenic influenza should not be unchanged if it increases risk of accidental release or misuse without correspondingly strong public health justification. Then should the research proceed with modification? For when it comes to research, yes, because modifications may include stronger oversight, enhanced containment, and then there'll be narrow experimental aims, independent review, and redesigning the experiments to answer scientific questions. Should research be restricted? Yes, categories of research should be restricted based on the biosafety or biosecurity concerns. That would include accidental release or misuse, or which undergoes rigorous scientific and public health justification. Should the research be halted? Or maybe in certain circumstances, temporary suspensions, but the scientific question cannot justify the risk. So there is always a safer alternatives. Containment or oversight and governance mechanisms should be thoroughly looked at. Yeah, that's it.
Oh, thank you. Thank you so much. Thank you so much. Can we have the next presenter? I see Fumi Raji. What group are you representing? I also see Andre. All right.
Okay, I'm representing group 3.
Okay,
right?
please go ahead. You
Can you
have
hear me?
2 minutes. Yes, we can hear you. Please go ahead. You have 2
Okay,
minutes.
so I'll just go straight to the what are the main dual use concerns? I'll highlight the points. Okay, one of it is the potential misuse of the research, because since everyone has people have access to this information, they can be misused. Then scientists or laboratory personnel are exposed to accidents. Yes. Then there's it could also weaken collaboration oversights. Then one of the important dual use of concern is also information security. So because almost everybody have access to sensitive data, so it is very, very necessary that you carefully consider what information is appropriate to share to the public. So then it will, in a way, to dash public confidence. So then to question 2, what are the potential public health benefits? So better understanding of the influenza would evolve. Then earlier detection of the virus with pandemic potentials. Then it will enable faster vaccine development. Then you have better risk assessment for public health authorities. So for question 3, what biosafety and biosecurity measures should be required? So for the biosafety aspect, it will be ensure personnel are trained and competent, then provide adequate PPEs, then you maintain emergency response plans and perform regular audits and inspections. That's a Then for the biosecurity, you'd have that secure storage of biological material. You control access to sensitive research informations is very key. Once your informations are very restricted, then you are very sure that your data are safe. Then you review publication and data sharing plans for potential dual use concerns. Then for your institution oversight, Institutional Biosafety Committee should review their reports almost like yearly. Then your dual use research review where applicable. Then the fourth question, how can the risks be reduced while preserving scientific value? So number one is provide additional training and capacity building. Yeah, training and retraining is very important so that you build capacity, and in a way too, it strengthens ethical values at your job. Then you carefully evaluate what information should be published to balance transparency.
Thank you.
Engage.
Thank you very
Yeah.
much.
So
Thank you so much.
yes, thank you. Yeah.
All right. Can we have Amma for group 7 and then Andre for what group is Andre representing?
Group 6.
Okay, please go ahead.
All right. Since we are running out of time, our group facilitator was Dr. Sharon, and scenario was about an AI-assisted design of drug resistance bacteria. So we were dealing with a biotechnology startup company that was there to design an AI that will combat against antimicrobial resistance. So the company was planning to release the AI model to an open software and to publish database containing all predicted resistance covering mutations and to make the dataset available for free for any other researchers. So the dual research for this, what are the dual major risks that we discussed was about this would be creation of superbugs. We can see that if once that particular information goes to the internet, it can accelerate bioweapons, whereby other researchers can re-engineer that particular data and create bacterial diseases, weapons to the other countries. And what governance measures would they recommend for them to be able to safeguard that particular information? They could make sure that they have restriction licenses for particular institutions that can be able to access that particular data, and lastly, which information can be controlled, and what should AI model be supporting data management possibly make sure that the organizations are really monitoring and observing the dual use research of that particular information not to be released. Thank you.
Thank you very much for that summary. Thank you. What group do we have next? We have group 7, Hammer. Please, can you unmute your mic and let's have your presentation.
Yes, can you hear me?
Yes, we can, absolutely. Please go ahead.
Yes. Yes, our scenario was talking about a biotechnology AI model predicting genetic mutation. The first question about the major dual use risk, and it is the predicting of a resistant gene and could transform the bacteria into antimicrobial resistance. And about the second question, the misuse, it could be about anticipating future resistance pattern and designing a new antibiotic before resistance emerging. And the governance measure, it should be applying a framework and implemented into this kind of research. And the open source and control access for the company as they are having planning the releasing of the AI model could be in open source and the software itself, but the resistance conferring a mutation, it should be in control access. and also not worldwide available. And also how to manage this, we should also apply the cybersecurity to prevent anyone to access for this information.
Thank you very much, Emma, for Group 7. Is there any other group that wants to present and we are here to call? If you know your group is supposed to present and we are here to call you, please use the raise hand icon. We're going to wait for about 10 seconds for that. All right, in the absence of none, I would like to bring the workshop to a close. Thank you very much to everyone. And I would like to invite Dr. Judith Okolo, the convener of this workshop, to give us a closing remarks. Thank you so much for staying till the end of the workshop and for participating in the stimulation exercise.
Thank you very much, Faith. Distinguished speakers and esteemed participants, colleagues and partners, gentlemen, ladies and gentlemen, as we bring this workshop to a close, I would like to express my heartfelt gratitude to every one of you for your active participation, your thoughtful contributions, both to the workshop and the hand stimulation exercise, and your unwavering commitment to advancing responsible science. Today's discussion has reinforced an important truth. Responsible science is not merely a technical requirement, but involves a shared responsibility and essential foundations for global health security. The knowledge and experience and ideas exchanged today will only make a difference if they are translated into action within our institutions, laboratory, and communities. On behalf of the Biosafe Advocacy Network, I extend our sincere appreciation to our distinguished speakers for generously sharing their expertise and inspiring us to their leadership. We're also deeply grateful to our Biosafe team, the volunteers, the supporters, and every participant who made the time to be part of this important conversation. At the Biosafe Advocacy Network, we believe that empowering students and young professionals is one of the most sustainable investments we can make in the future of responsible science. Together, we are building a new generation of leaders who will champion biosafety and biosecurity across Africa. As we live today, let us remember that every safe laboratory practice, every ethical research decision, every risk assessment conducted, every young scientist we mentor contribute to a stronger and more secure future for all. I encourage us all to be ambassadors, become ambassadors of biosafety and biosecurity. Thank you all. God bless you. And we look forward to seeing all of you in our next workshop, and we hope you feel the feedback from us. Thank you all. Over to you, Faith. Thank you.
Thank you so much. Thank you, Dr. Judith, for that beautiful closing remarks. And a big thank you to everyone. Like we mentioned, kindly fill in the workshop so it can enable us to have a better preparation next time we're having another workshop. So thank you for your participation, for your time. Thank you so much. And as we move on to the end of the workshop, I would like us to switch on our videos as we take a picture. If you don't mind, kindly switch on your videos so we can take a good picture. Thank you. Thank you. I can see our appreciation. Thank you. We are glad that you are here. So please switch on your videos. Okay, we are waiting for other persons. Please switch on your videos and we'll go now. Let's smile on the count of 1, 2, 3. Thank you very much. And with this, we've come to the end of the workshop and we officially close the workshop. Thank you very much. Like I mentioned, I would like to mention a few announcements. Firstly, the presentation slides and other resources will be made available to all registered participants. Once again, the WHO academic course is a prerequisite for getting the certificate of participation. The recording of this workshop will be made available on our YouTube channel at Biosafe Advocacy Network. Also, every question that was not addressed will be addressed and will be sent to our emails where we are sending the workshop certificates. Once again, we want to tell you, thank you for staying tuned to the end.
How about the materials?
Yeah, the materials will be sent to our email address to all registered participants. And for everyone that joined with a name different from their registration name, please rename yourself so we can identify you. So if you are named with something like Infinix, please rename yourself to your actual full name that you used to register. Like I said once again, all the resources will be made available to be sent to our email addresses, and the recording of this workshop will be available on our YouTube channel at Biosafe Advocacy Network. Thank you very much and have a wonderful day ahead. Bye.
Thank you. Thank you.
Thank you. Bye, everyone.